Millions of years ago, Earth created holes in the ocean floor so deep they could swallow Mount Everest whole and still have room to spare. What seemed to be just dark, cold water turned out to be a world of pressure so strong it would crush your body in seconds, a force 1,000 times greater than the weight of a car on every inch of your skin. The Mariana Trench, the deepest of all, is 11,000 meters deep, where water becomes so heavy it turns into something almost solid. But here's what keeps scientists awake at night. Each ocean trench kills in a different way. Some freeze you in water almost at the point of turning to ice. Others crush you so fast you become the size of a marble. This forces us to ask a terrifying question. How many different ways has nature created to end human life in the deepest, darkest places on our planet? Subscribe to the channel, leave your like and comment what part of the world you're watching from, because now I'm going to tell you everything. What really happens to a human body if it could somehow be dropped into the deepest ocean trenches? The short answer is that pressure rules everything there, and it is not an environment the human body can negotiate on its own. The Hadal Zone begins around 6,000 meters below the surface, and by the time you get to the very deepest trenches, the pressure rises past 1,000 times the air pressure you feel at sea level. That load is not exotic or sudden down there. It is simply the weight of all the water above, increasing by about 1 atmosphere every 10 meters. Those are ordinary-sounding steps, but they add up fast, and they set the basic limit on what living tissue and any trapped gas can tolerate. Human tissues are mostly water and are only slightly compressible, so the bulk of your muscles, skin, and blood does not crush in the cartoon sense. Underwater, pressure is applied evenly in all directions, which means solid and liquid parts of the body share the load without obvious deformation. The real weak points are the air spaces. Your middle ears, sinuses, lungs, and even small pockets of gas in the gut have to match outside pressure as you descend. At shallow depths, you can equalize the ears by swallowing or pinching your nose and gently blowing. Your sinuses usually follow along, but the lungs and the rest of the body have limits that you cannot push very far, and those limits arrive long before the Hadal Zone. Air compresses as pressure rises. If you take a lungful of air at the surface and dive down, that air shrinks as outside pressure climbs. The deeper you go, the smaller the lung volume becomes until the soft tissues reach their structural limits. Experienced freedivers know this line because they feel the chest become stiff and the urge to equalize never quite satisfies. Past a certain point, tiny blood vessels can rupture, fluid can seep into the airways, and breathing is no longer possible even if you had a regulator. This is why unprotected exposure beyond a few dozen meters is already risky for the lungs and the ears, and why a few hundred meters without a pressure-maintained environment is a lethal proposition. Now scale that to the Hadal Zone. At 6,000 meters, the outside pressure is hundreds of atmospheres. At the very deepest points, it pushes past 1,000 atmospheres. No unprotected human can survive that. If exposure happens gradually in open water, the failures arrive well before you get there through ear and sinus barotrauma, lung collapse, and hypoxia, which is the simple lack of oxygen. If exposure happens suddenly because a submersible hull fails, the time scale is so short that there is no moment of awareness. Water rushes in at extreme speed, the pressure equalizes almost instantly, and the human inside does not perceive pain or fear. It ends before the brain can register anything. People often imagine bones shattering or the heart being crushed, but that is not how uniform pressure works. Your heart and blood vessels are closed, fluid-filled systems, and fluids transmit pressure evenly. The problem is that airspaces collapse, gas exchange stops, and critical tissues are starved of oxygen. As the lungs shrink, tiny sacs called alveoli flatten and can stick shut. The lining can tear and fluid leaks in. The right side of the heart faces a rising load from blood shifting into the chest, while the left side cannot fill properly. The brain fades within moments when oxygen falls, and at extreme pressure, this process is so fast and overwhelming that conscious perception does not keep up with events. The ears are a good example of how pressure defeats us. The middle ear is an air-filled cavity that connects to the throat by small tubes. To avoid pain on descent, you push a little air into that space so its pressure matches the water outside. If you cannot do that fast enough, the eardrum bows inward, vessels rupture, and it can tear. The deep ache called a squeeze becomes sharp and disabling. A similar thing can happen in the sinuses, where trapped air pulls on delicate linings and causes bleeding. These injuries are survivable at modest depth, but they are early signals that the pace of pressure change has exceeded the body's ability to keep up. The only practical way for a person to visit Hadal depths is to ride inside a machine that holds the inside near the same pressure as the surface. Submersibles and rigid atmospheric diving suits do exactly that. A strong hull keeps the water out, seals maintain integrity at the joints and viewports, and life support keeps the air breathable. Inside, your body stays at roughly 1 atmosphere, the same load it handles every day. That controlled bubble is what separates a calm descent from a fatal one. Even the best scuba gear is not enough at those depths because the gas becomes so dense that breathing itself turns into work your lungs cannot do, and the intoxication and toxicity risks skyrocket. When the pressure around you rises, every breath you take gets heavier because more gas molecules are packed into the same space. A breath that felt easy at the surface can feel like pushing syrup through a straw after only a few dozen atmospheres. On top of that, nitrogen in ordinary air acts like an anesthetic at high pressure, clouding judgment. If you raise oxygen too much to compensate, it becomes toxic and can trigger seizures. Switching to helium as a breathing gas helps with narcosis and density, but then a separate problem called high-pressure nervous syndrome appears, with tremors and reduced coordination. All of this unfolds long before you even approach hundreds of atmospheres, which is why Hadal depths demand sealed habitats. That relentless pressure is the one constant across every trench on the planet. Whether you are above the Mariana, Tonga, or Puerto Rico trenches, the numbers change by a few hundred atmospheres, but the experience for human tissue is the same story of gas collapse and fluid dominance. Even after death, pressure shapes what happens next. Bacteria that break down tissue produce gases, but those gases dissolve more readily when the pressure is high and the water is cold. The usual bloating that can make a body float in shallow water is muted or absent. Air that once kept you buoyant is long gone, replaced by liquid and compressed soft tissue, and the result is a heavy, compact mass that tends to stay down. It is worth separating two different pressure problems that people sometimes mix up. Divers who breathe compressed gas at depth have to worry about decompression on the way back up because dissolved gases can form bubbles as pressure falls. None of that applies inside a 1-atmosphere submersible because your body never experiences the external load and you are not breathing dense gas. The other problem is compression itself. If you are exposed to rising pressure without an enclosing shell, you cannot breathe, you cannot keep air spaces open, and tissues begin to fail. Engineers have dreamed about liquid breathing, where the lungs are filled with oxygenated liquid to avoid gas collapse, but keeping someone alive that way at hundreds of atmospheres is far beyond current medicine. Because pressure rules everything down there, it also sets the strict rules for how machines must be built to carry people safely. Designers choose thick spheres or near spherical shapes because that geometry spreads the load evenly. Every port, bolt, and seam is a potential weak link that must survive a force that never stops pushing. If the system works, the person inside can be comfortable in a t-shirt at 1 atmosphere while the ocean outside presses with hundreds to over 1,000 atmospheres. If the system fails, the outcome is determined by that same difference. The ocean does not haggle or hesitate. It moves to fill the space immediately, and the body inside is not a factor in the equation. When people ask what it would feel like to die in a trench, the answer is that pressure removes feelings entirely from the equation. In slow, unprotected descents, injury and suffocation arrive early. At depths humans can reach briefly, and they end awareness before Hadal numbers come into play. In sudden failures at depth, the transition is fast for sensation. Either way, the governing factor is the simple arithmetic of water stacked above you, adding about 1 atmosphere for every 10 meters. Human organs that depend on airspace, especially the lungs and ears, cannot keep up, and neither grit nor training changes that. The Hadal realm is not hostile by intent. It is indifferent. It allows us in when we bring our pocket of the surface with us, and it makes no exceptions for the body when that pocket is lost. If the only way to be there is to carry a small slice of surface conditions with you, the next practical question is what the long trip downward actually looks and feels like, layer by layer, as the ocean changes around the vehicle and anything else that is descending. The vertical path is not a featureless drop. It is a series of zones with distinct light, temperature, chemistry, and biology, and those differences matter because many important processes play out well before the deepest trenches come into the picture. Understanding that structure turns a vague idea of going down into a clearer picture of what really happens along the way. Near the surface, you are in the sunlit layer where photosynthesis works and where most of the familiar ocean life stacks up. Waves mix this zone, which often extends a few dozen to a few hundred meters depending on winds and seasons. Colors are still there, but red wavelengths are the first to fade because water absorbs them efficiently, so anything red turns dark and then black as you descend. The water can look brilliantly clear or hazy with tiny particles, and that clarity is local and temporary. Fish, plankton, and jellyfish are abundant here, and a vehicle's lights or sounds can draw curious visitors. It is also the most turbulent slice of the ocean, with currents that shift over short distances and time. For a body or an object entering the water, this is the stretch where some trapped air still matters for buoyancy and where clothing and gear can either slow sinking or encourage an early plunge. Drop below the sunlit layer and the world turns into a steady fade. This twilight zone reaches down to around 1,000 meters. The temperature falls quickly across the thermocline, which is a band of rapid cooling that often sits within the first few hundred meters. By the time you are a few hundred meters down, it can feel like moving from a cool room into a refrigerator, and by roughly 1,000 meters, the water temperature is commonly around 2 to 4 degrees Celsius. Light dwindles so much that your eyes have nothing to adapt to anymore, and bioluminescence becomes the main source of visible flashes. Many animals here make their own light, usually in the blue to green range because those colors travel best underwater. Submersibles often see little bursts when the hull or a fin of the vehicle disturbs plankton or small crustaceans that use light to startle predators. Sound begins to matter more than sight because it travels far and fast in cold, dense water. Instruments switch from cameras to sonars and hydrophones to understand what is nearby. Within this twilight band lies another shift, the oxygen minimum zone. That is the stretch where oxygen can be low because surface waters rich in tiny organisms sink or are transported downward, and bacteria and animals consume the oxygen as they respire. The exact depth depends on the region, but it often sits between a few hundred and several hundred meters, and sometimes deeper. In these layers, animals adapt by slowing metabolism, developing efficient gills, or avoiding the zone entirely during the day and crossing it at night. For a body moving through, low oxygen slows some microbial activity, but it does not halt it, and large scavengers that tolerate low oxygen can still feed. Chemically, these waters can carry higher levels of dissolved carbon dioxide and nutrients regenerated from decaying organic matter, and those compounds influence which microbes dominate once tissues begin to break down. Past the twilight comes the deep ocean proper, the bathypelagic. Down here, from around 1,000 to a few thousand meters, darkness is complete. The temperature settles into a narrow, cold band. The swell and short-period waves that surface sailors care about are gone, replaced by slower, steadier currents that can persist for long distances. There is a faint, widespread band called the deep scattering layer, which is not a solid structure but a mass of animals that are dense enough together to reflect sound. Many of them migrate toward the surface at night and back down during the day, and a vehicle can move with or through this living cloud. Bioluminescent animals get larger and stranger, with squids, ctenophores, and comb jellies that can light up like signs. Outside the hull, the pressure continues to rise by roughly 1 atmosphere every 10 meters, but inside, a proper submersible, the air stays at around 1 atmosphere, and the growing load is felt only as a slightly louder background creak and higher demands on the mechanical systems that resist the outside force. Around 4,000 to 6,000 meters, you transition into what oceanographers call the abyssal zone. The seafloor becomes a real presence because the average depth of the global ocean sits in this range. If you are above an abyssal plain, the bottom is wide, flat, and covered with fine sediments that accumulate grain by grain over long times. If you are over rougher terrain, the bottom can be cut by hills, ridges, or scars from ancient slides. Near the bottom, currents can accelerate, lifting clouds of silt in events sometimes called benthic storms. Those are not storms in the usual sense, just faster near-bottom flows that can last days and move a lot of sediment. A body or an object on its way down might be diverted by these bottom currents, nudged sideways into a gully, or slowed temporarily by turbulence that increases drag. Gases produced by decomposition are less likely to form buoyant bubbles here, both because the water is cold and because pressure keeps gases dissolved. That means refloating is rarely an issue in deep water the way it can be in shallow lakes or coastal seas. Once you pass about 6,000 meters, you are in the hadal zone, which means trenches and their adjacent slopes. The geometry changes from broad plains to steep walls and narrow floors. The inner wall of a trench can be nearly vertical in places, broken by ledges and terraces formed by slumps and faults. The floor might be a ribbon of sediment, or it could be rougher and patchy with blocks that tumbled from above. A lot of descending material never reaches the deepest line of the trench because it catches on those slopes or settles on a terrace layer that is stable for years at a time. If a person were inside a working vehicle, the pilot would be balancing ballast and thrusters to keep the descent controlled, aiming to avoid rock faces that shed debris. If it was a body or a disabled system sinking freely, the path down would be set by simple mechanics. Weight compared to displaced water, how streamlined or bulky the shape is, and what currents happen to be doing in that spot. The physics of that motion is basic but powerful. Things sink until the upward push from the water equals their weight. That is buoyancy, and it depends on how much water is displaced by the shape. Water density changes a little with temperature and salt content, but not by a lot, so the main variables are shape and what gas is trapped inside. Clothes that trap water and swell can increase effective size and slow descent. Tanks, weights, and tethered gear add mass and can carry remains swiftly down. As speed builds, resistance from the water grows until it balances the pull of gravity, and then the object falls at a steady speed. For a human without an active airspace, the tendency is to sink and keep sinking. The only real unknowns are how straight the path is and what obstacles are in the way. As sight fades with depth, sound becomes the practical tool for navigation. The speed of sound in seawater is affected by temperature, salinity, and pressure, so it typically increases with depth after a certain point where colder temperatures stop dominating and pressure takes over. There is a depth range where sound can get trapped and travel long distances with little loss, often around a few hundred to about 1,000 meters, called the sound channel. Submersibles use acoustic beacons and transponders to know where they are when GPS signals cannot reach them. If communications fail, those acoustic tools are still the best chance to estimate position or guide a later search. For a falling object, the background sound does not alter the path, but it does shape how quickly searchers might detect it after the fact, and from how far away. Temperature is a constant presence in this story. Surface waters can be warm or chilly depending on latitude and season, but once you are in the deep ocean, the range collapses to a narrow band near freezing without actually freezing. Body heat is lost quickly because water draws it away much better than air. In a vehicle, insulation and heaters keep people comfortable, but taking a gloved hand to a viewport will immediately remind you how cold the outside really is. For a body, the cold slows many chemical reactions. Microbes still work, but the pace of tissue breakdown is reduced. That slower chemistry and the suppression of buoyant gas bubbles are the main reasons remains in deep water behave differently from what we see closer to shore. The way light behaves explains a lot about what you see during descent. Red light disappears first, then orange and yellow, and blue goes farthest. That is why most bioluminescence is blue or green. Animals down there are tuned to that band because it is efficient to make and it gets noticed. When a vehicle moves, it triggers little flashes as bodies brush past or as animals react to disturbance. Cameras need their own lights, and those lights change behavior around them, drawing in curious fish or warning shy ones away. If you switch the lights off, the darkness is complete, but the microphones keep telling you the ocean is still active, from the faint crackle of sediment to the sound of water flow over the hull. Chemistry shifts gradually with depth too. Surface water exchanges gases with the atmosphere, and plankton fix carbon and release oxygen during the day. Deeper down, CO2 builds as respiration dominates, and oxygen can be limited until mixing brings fresher water in. The pH, which is a measure of acidity, is slightly lower in deep water because of that extra dissolved carbon dioxide, though the difference is not dramatic to our senses. Salinity is fairly steady in the deep ocean globally, with regional variations set by large-scale circulation. None of this changes the basic fact that the deep ocean is cold, dark, and under pressure, but it shapes which animals live where, how active microbes are, and how quickly soft tissues disappear. The time it takes to reach the bottom depends on how far you are going and what you are in. Crew vehicles designed for trenches take many hours to descend and ascend because safety demands careful control and because moving quickly through water at depth is expensive in energy and stressful for the hull. An unpowered descent of a weighted probe or a heavy piece of debris is faster but still measured in long stretches because water resists motion strongly once speeds climb. Bodies without heavy attachments descend more slowly than the same bodies tethered to gear, and they are far more likely to catch on a ridge or get pushed into a side valley by a current they cannot overcome. That is why even in narrow trenches, the deepest axis often receives less material than you might expect. Biology reacts to all of this in predictable but still interesting ways. In upper layers, predators and scavengers are abundant and rapid. In the oxygen minimum zone, some big animals are scarce, but specialized ones take their place. In the deep and abyssal zones, food is so rare that anything substantial arriving from above is noticed, sometimes within minutes to hours, by amphipods and other scavengers that can follow faint chemical trails in the water. By the time you are in Hadal depths, those same families dominate the first wave of consumption, while larger fish, where they occur, arrive more sporadically. The colder it is, the more the balance tips toward animal feeding over microbial decay in the early days, with microbes taking over the slower finish. There is also the reality that the ocean is not still wallpaper on the way down. Internal waves, which are slow wave motions inside the ocean layers, can push water up or down by tens of meters without rippling the surface. Eddies shed by boundary currents can drift through the water column and change conditions over days to weeks. A descending vehicle might cross a layer where temperature, turbidity, and current direction all change within a few minutes. These are not dramatic shifts, but they add unpredictability to exact paths and to how long you spend in each zone. For a body falling without guidance, such shifts can be the difference between sliding smoothly into a trench axis and being pushed onto a terrace where it stays. By the time you imagine reaching the trench floor, the story already includes a lot more than darkness and pressure. The ocean has stripped away color, bled heat from anything warm, muffled direct vision, and made sound the reliable channel. It has selected which animals are present, and it has set the rules for buoyancy and motion that decide where moving things end up. The descent is not a straight, featureless elevator ride. It is a layered journey where each band contributes something different to the outcome, whether the traveler is a person inside a well-built sphere, a body without protection, or a small machine taking measurements on the way to a steep, shadowed slope. By the time you picture that layered drop through fading light and colder water, it becomes easier to sort out how things actually go wrong because the environment narrows the options. In real operations, the fatal outcomes fall into a few straightforward paths. People drown in the upper ocean where water gets into airways. They suffer pressure damage during an uncontrolled descent that overwhelms the body's ability to adjust, or if a pressure hull fails at great depth. The event is so fast there is no moment to register anything. That sounds simple, but each path has its own mechanics and its own triggers, and most of them play out well before a trench floor ever comes into play. Start with drowning because, statistically, it sits at the front of the line. In the ocean, drowning doesn't require extreme depth, complicated gear, or unusual biology. It just needs water to reach the lungs while the person is unable to keep breathing effectively. The chain often begins with something small and ordinary: a wave over the face during a transfer from deck to water, a valve or hose that fails and floods a mask, a tangle in a line that traps a swimmer, or a misstep in heavy clothing that turns a fall into immersion. Cold water makes all of that worse. At immersion, a reflex called cold shock pulls a sharp gasp, speeds up breathing, and spikes heart rate. If your face is under when that gasp hits, water can be inhaled before you even think about it. Over the next minute or so, you fight the urge to breathe too fast. Your muscles clench, and any fine motor task becomes harder. If you are wearing gear, even something simple like a weight belt or a tangled tether becomes an obstacle you cannot solve smoothly. Once water enters the airway, the body tries to protect itself. The vocal cords can clamp in a reflex called laryngospasm, which blocks more water but also blocks air. That can last seconds to tens of seconds, and while it protects, it also drives oxygen down. Eventually, the reflex relaxes, or you fight past it, and at that point, water reaches deeper into the lungs. Coughing and gasping draw more fluid in, gas exchange fails, and oxygen in the blood falls. Most people lose useful consciousness within a few minutes of true submersion. Cold stretches that timeline a little in some circumstances, but cold shock up front usually cancels that advantage. Cardiac rhythm becomes unstable as oxygen drops and carbon dioxide rises, and the heart may go into an arrhythmia before stopping. In rough water, waves can keep you from getting a clear breath even if your face breaks the surface, and panic accelerates the slide because coordination is lost. Compared with a pool or a sheltered cove, the open ocean adds motion and noise that distract and delay. The nearest solid thing to hold is often far away. A life jacket or buoyant suit changes the story by keeping the airway clear long enough for rescue. Without that, the window is short. In trench work specifically, drowning mostly happens long before anyone is near hadal depth. It happens during launch and recovery, during transfers, or during surface and shallow operations, where human contact with the water is inevitable. Once something goes very wrong at great depth, like a submersible failure, drowning is not the process anymore because pressure dominates first. Pressure damage, the broad category called barotrauma, shows up when pressure changes outpace equalization and tissues fail. The word sounds technical, but it just means injury from pressure. The ears and sinuses are the classic examples during descent. If you go down faster than you can push a little air into those spaces, the outside pressure bows soft tissues inward and ruptures small blood vessels. Pain escalates. Your inner ear can be affected enough to cause severe vertigo, and you lose the ability to orient. A ruptured eardrum is not automatically fatal, but paired with cold, disorientation, and breathing gear to manage, it becomes a potent trigger for drowning. Masks and suits also matter here. A tight mask that is not equalized can bruise the face and leave eyes bloodshot and swollen. A minor-looking but distracting injury nicknamed mask squeeze. A dry suit that does not admit enough gas on the way down will pinch skin and soft tissue, and in severe cases, it can trap you in a posture where you cannot move well or reach valves. These are injuries of inconvenience until they combine with stress and limited dexterity to create larger problems like an uncontrolled free fall or an inability to manage buoyancy and breathing. In diving, the fix is to descend slowly and equalize often. In a forced, rapid descent, those small steps disappear and injuries multiply. The lungs sit at the center of pressure problems when gas is involved. There are two very different cases. In breath-hold diving, the air you took at the surface shrinks as you go down. At modest depths, the chest feels tight but manageable as blood shifts to the core to compensate. Push deeper, and the lung tissues themselves become the limiting factor. Capillaries can leak, tiny sacs where gas exchange happens can collapse, and you can cough blood, feel weak, and black out. That is lung squeeze. In scuba, very deep descents used to be limited by narrow breathing passages in old equipment, but modern regulators deliver gas fairly easily. The problem there is different. The gas you breathe becomes dense enough that moving it takes work. You can end up with carbon dioxide building in the blood because exhalation isn't clearing enough, a state called hypercapnia. It makes you feel air-hungry and confused at the very time you need to slow down and fix things. On top of that, your ability to equalize ears and sinuses can fall behind as descent accelerates. In both breath hold and scuba, a bad descent does not need the abyss to become fatal. Dozens of meters are enough if injuries and confusion stack. There is a related but less common scenario in hard suits and helmets. An atmospheric diving suit is a rigid shell that keeps the inside near surface pressure. It has joints you move like a robot's. If the suit cannot compensate properly, or if a valve or seal lets ambient pressure rise inside the helmet or suit faster than you can respond, the pressure change is transmitted straight to the body. You cannot equalize fast enough, ears and sinuses fail, and if water intrudes, you can drown inside the shell before you can reach a flood or jettison lever. Engineers design multiple backups to prevent that, but the pathway is conceptually the same. Pressure outpaces physiology, then water reaches the airway, then hypoxia ends awareness. People often ask about decompression sickness in this context, the bends, where dissolved gas forms bubbles as pressure falls on ascent. That is important in many diving accidents, but it is not the main story in an uncontrolled descent in the huddle context. These trench scenarios are about going down too fast, not coming up too fast. The immediate risks are ear and sinus damage, lung squeeze or gas density issues, and drowning. If a diver somehow reversed and rocketed to the surface after breathing dense gas at depth, then decompression and arterial gas embolism become major concerns, but that is the ascent side of the curve. Then there is the scenario that occupies people's imaginations because it is so absolute, a pressure vessel failure at depth. Inside a functional submersible or a passenger sphere, you live at close to 1 atmosphere, while the water outside pushes with hundreds to over 1,000 atmospheres. A hull is a boundary that holds those worlds apart. If it fails catastrophically, the boundary is gone, and the system tries to equalize instantly. Water is incompressible in everyday terms and accelerates into the opening at extraordinary speed. The timescales we are talking about are measured in fractions of a millisecond, shorter than the time it takes a human nerve to carry a signal from hand to brain. Inside, the pressure spikes, structures shatter, and the contents are swept and heated by the energy released as the pressure difference disappears. There is no period of fear, no chance to take a breath, no conscious perception. The event is over before sensory systems can register it. That is not an attempt to make it dramatic or to soften it. It is just what the physics says when a large pressure difference collapses. Less dramatic failures inside a vehicle are possible, and they are often survivable in shallower operations. Smoke or a battery fire in a sealed cabin, a carbon dioxide scrubber problem that lets CO2 climb, a small leak that can be managed with pumps. Those matter a lot in safety planning, but in the Hadal context, the catastrophic hull failure is the one that explains why pressure dominates the conversation. It is the scenario where depth itself, not heat, not toxicity, not lack of air, is the cause. When it happens, it defines the outcome in microseconds. Chemical hazards are part of the deep sea, but next to pressure and water itself, they are side notes for humans. Near some trench margins, cold seeps release methane and hydrogen sulfide. Hydrogen sulfide in particular is toxic because it interferes with cellular respiration. A diver in ordinary gear who swam through a dense plume could be overwhelmed, but in practice, no one is swimming around unprotected at 6,000 meters, and vehicles are sealed. If a vehicle's life support failed and let gases accumulate, that would be a cabin problem, not something coming from the outside seawater in a trench. Other chemical oddities like very high pH fluids in serpentinite areas exist, but they are relevant for microbes and clams, not for a person inside a pressure sphere. So while it is correct to say toxic fluids can be lethal, the realistic ranking puts pressure problems and drowning far above chemistry for human risk. If you compare trenches in different parts of the world, the interesting differences show up in what sets off the chain of events, not in how the body is injured. Steep inner walls in one trench make entanglement and collisions more likely during a descent or a bottom approach. Broad, sedimented terraces in another trench increase the chance that a descending body or broken gear ends up stranded above the axis, which can complicate recovery but does not change the cause of death. Earthquakes are common along subduction zones. A small one at the wrong time can throw a vehicle against a slope or trigger a turbidity flow that blinds sensors and buries lines. Strong boundary currents and internal waves differ from place to place and can surprise pilots with unexpected pushes or lulls. Those are the triggers. The outcomes still reduce to drowning, pressure damage during loss of control, or an implosion if the hull fails. Timescales help make this concrete. A struggling swimmer or a diver with a flooded mask can lose consciousness in a few minutes, especially in cold water, and is gone within several more unless supported. A rapid descent without equalization injures ears and sinuses in less than a minute and can create disabling vertigo that leads to drowning shortly after. Hypercapnia from dense breathing gas on a hard-working descent can fog thinking within minutes and drive misuse of gear that speeds the accident. An implosion at depth removes awareness essentially immediately. In all of these, there is usually a brief window where a calm, trained response can stop the slide, which is why procedures focus on small, practiced actions. Slow the descent, equalize often, fix the flood, drop weight, follow the line. In trench operations, the environment shortens the window, but it does not change the physics. One practical question people ask is whether a person would sense a barotrauma event and how it feels. Ear barotrauma is pain and pressure that escalates quickly. People describe it as a deep ache that turns sharp, followed sometimes by a pop and relief that is actually a rupture. Sinus barotrauma is a face and forehead pain with bleeding. Lung squeeze is a deep chest tightness and sometimes a cough that brings up pink froth, a sign of fluid in the lungs. Hypercapnia feels like panic because it stimulates the drive to breathe, even when you are already breathing fast. None of this is mysterious. If you have been in a pool with a cold and tried to dive to the bottom, then multiply by speed, depth, and the task load of real equipment. Add cold water and the mental bandwidth shrinks. Small errors multiply quicker than people expect. Inside vehicles, warning signs for the catastrophic case are usually subtle until they are not. Engineers listen for new creaks, change missions if a seal looks suspect, and watch for odd readings in pressure and humidity. A leak discovered early is often containable. The risk profile changes as you head deeper because the margin for unknown defects narrows, but the behavior up to the moment of failure is often normal. That is why crews rely on checklists and conservative decisions rather than intuition. By the time a hull fails, there is no intervention left to make. The best defenses were earlier, in design, inspection, and in refusing dives that feel rushed or compromised. If there is a thread that connects these scenarios, it is that water and pressure do not negotiate. Drowning is water finding an airway. Barotrauma is pressure changing faster than the body can compensate. Implosion is pressure erasing a boundary. The ocean adds currents, darkness, and cold that make self-rescue harder, but it does not add new kinds of death at depth. The same few pathways repeat, shaped by immediate circumstances. On the way down through the water column, most of the danger to the person, not the machine, is front-loaded in the first hundreds of meters. At great depth, the person's fate is tied to whether the machine keeps that small pocket of surface world intact. If it does not, the end is certain and swift. If water intrudes earlier, the game is back to airways, breathing, and keeping control long enough to get out of it. If the ways a life can end are simple, the place where it ends is not, and that matters because the ground under all that water is active. Even when a machine holds its pressure and the people inside do everything right, the shape and behavior of a trench can turn a routine plan into a risky one. A trench is not just a deep spot, it is the mark of a subduction zone, where one tectonic plate slides under another. That setup builds steep inner walls, fractured floors, and a constant background of small earthquakes with the occasional larger one. Those ingredients create mechanical hazards that are different from the open abyss and directly affect where anything descending will travel and where it will stop. Picture the inner wall of a trench as a long, tall slope made of layered sediments that have been scraped, folded, and faulted by the grinding of plates. Some sections are solid rock, but much of it is a mix of muds, sands, and broken bits packed together under pressure. Water moves through those sediments and can build up in tiny spaces between grains. When that pore water carries enough pressure, it weakens the bond holding grains together. The slope can let go suddenly and slide. When it does, the moving mass churns up the seafloor and mixes with water, turning into a dense, fast, sediment-laden flow called a turbidity current. That name sounds technical, but it simply means a cloud of mud and sand that is heavier than the clear water around it, and that therefore keeps flowing downhill along the bottom. Those bottom flows are the ocean's freight trains. They move faster than a person can swim and much farther than a surface wave can carry a single clump of mud. In past events documented by snapped telegraph cables, such as the well-studied case off the Grand Banks in the year 1929, these currents traveled many tens to hundreds of kilometers and broke lines one after another as they passed. In trenches, the path is tighter and steeper, so the same physics concentrates the energy downslope. For a submersible near the bottom, a turbidity flow is a real threat. It can reduce visibility to 0 in seconds, push the vehicle sideways, and bury lines or instruments. For a body or debris descending without control, arriving in the middle of one of these events means burial under centimeters to meters of fresh mud within minutes. That is not speculation. Lander experiments that drop baited cameras to the seafloor have recorded scenes that go from a clear view to a brown slate in a short time when a slide strikes. The trench floor itself is not always a clean ribbon. It often carries fault scarps, which are small cliffs formed when the seafloor breaks and shifts. It can be dotted with blocks that have toppled from above, with sizes ranging from stones to boulders large enough to count as small hills in that context. Between those obstacles sit patches of soft sediment. Thrusters on a submersible can dig into those patches and kick up a dense cloud that blinds cameras and lidars, and once the fine particles are in the water, they take a long time to settle. The safer tactic is to keep a few meters of altitude and resist the urge to settle on the bottom, unless there is a specific reason, because getting moving again from soft mud can require more thrust and buoyancy than is available. Terraces complicate the picture even more. The inner walls of many trenches are not smooth. They are stepped by ancient slumps into benches. Each bench can act like a shelf that catches anything moving from above. Think of a gully that funnels small objects down until they hit a ledge and stop. That is why many things never make it to the deepest axis. Bodies, equipment, and fragments can halt on these shelves and sit there for years, visible to scavengers and to vehicles that pass, and then vanish under a new layer when the next slide comes. Aftershocks following a main earthquake can jog the slope and trigger smaller failures. Those aftershocks often continue for days to months. The same layer that just buried something can be partly removed by a later slump that plucks chunks of the fresh deposit and drops them farther down. Over a few years, burial and exposure can alternate several times, like a slow-motion shuffle. Another feature that shows up along many trench margins is cold seep activity. Fluids rich in methane and other compounds migrate upward and seep through the seafloor. Where fluids exit, they can weaken sediments by raising pore pressure or by creating slippery layers. In some forearc regions built of serpentinite, the rising fluids are very alkaline and carry fine clay. Mud volcanoes a few meters high dot those slopes, extruding weak, pasty material. Submersibles that land on such patches can partially sink and need careful use of ballast and thrusters to get free. Tethers dragged across seeps can cut channels and get stuck when the soft material collapses around them. None of that is dramatic on video, but it is exactly the kind of quiet hazard that ties up a mission and increases risk as pilots and crew try to recover. The geometry of the trench also controls currents. Narrow, V-shaped sections focus downslope flows into a central axis. Broader, more filled trenches act like a series of terraces and moats. In the narrow case, debris and remains are more likely to be funneled toward the deepest line, though even there, local knobs and blocks can trap things in small side pockets. In the filled case, material tends to strand on higher steps. There are good examples of both styles in the Pacific, where some trenches show a crisp, narrow groove, while others are smoother and broader because rivers from nearby continents have fed them a steady diet of sediment over geologic time. That difference changes where a search might make sense and how easy it is to move around without snagging. Snagging deserves its own attention because umbilicals and tethers are a constant reality for remotely operated vehicles and sometimes for deep instruments. A tether that crosses a sharp rock can abrade and fail faster than people expect because the vehicle moves with currents and the line soars back and forth under tension. Simple geometry can trap a line if it drops into a notch, and the vehicle then drives past a point of no return without noticing. Pilots manage this by hovering above the seafloor, keeping careful track of heading changes, and avoiding undercut ledges where a line could slip behind the vehicle. In trenches, those undercuts and notches are common. Faults and slumps carve them in abundance. If a line snags and cannot be freed, the vehicle may need to drop weights and cut free. The topside team then hopes the acoustic release does its job and that the rising section does not meet another snag on the way up. Rockfall is less predictable but just as real. Even a small clast rolling down a slope can damage a propeller, a thruster guard, or a viewport if the timing is bad. Crews listen for faint pings on the hull that suggest small grains are hitting, which can warn that a larger fall is underway somewhere upslope. The problem is that sound travels well and echoes, and triangulating in real time is hard. The practical choice is to stay out from beneath steep scarps whenever possible and to keep excursions short when a closer approach is needed for a sample. Many mapping efforts plan transects that run parallel to the slope rather than directly upslope or downslope to limit the time spent in the path of gravity. There is also a quiet hazard in soft sediment called suction. When a heavy object presses into fine mud, water is squeezed out and a low-pressure pocket forms beneath it. If you try to lift straight up quickly, the mud resists because water needs time to flow back under and equalize the pressure. Vehicles that have settled into very soft beds sometimes need to roll or rock gently and add buoyancy slowly rather than yanking upward. A stranded body or piece of equipment can become partially embedded the same way. If a slide then runs across that spot, the object is even more likely to stay because the moving mud will flow around the anchored shape and leave it buried. Seismicity deserves a clear-eyed view. Subduction zones produce frequent small quakes and occasional larger ones. Even a modest event felt as a long, slow shudder at the seafloor can release enough energy to trigger slope failures or to shake a delicately balanced stack of sediments into motion. The timing is not predictable on human scales. The fact that a site was quiet yesterday does not promise it will be quiet today. For operations, that uncertainty drives conservative choices, like keeping dives shorter than the weather or fatigue would otherwise allow, and placing long-term instruments on more stable benches rather than on the steepest faces. For the fate of remains, it means that a calm, exposed resting place can change without warning into a buried one, or vice versa, as earthquakes reshuffle the near-surface layers. Navigation tools have their own quirks in these environments. Acoustic positioning that works well over a flat plain can become patchy in a trench where walls reflect and scatter sound. A range reading might bounce the long way around a bend and come back late, making a vehicle think it is farther away than it is. Sonars that map the bottom can show confusing shadows where overhangs hide pockets and small bowls. LiDAR, the laser-based mapper, is often useless beyond a short distance in turbid water. Pilots compensate by adjusting sensor ranges, changing altitude, and cross-checking instruments rather than trusting one readout. But these adjustments take time and attention, which are the same resources needed to manage the tether, the samples, the ballast, and the plan. The point is that geology and mechanics do not just shape the bottom, they seep into every part of how you move and decide. For a body descending without guidance, all of this means the final position is dictated more by slopes and flows than by the initial drop point. Currents can push sideways in the water column, but near the walls, gravity and the shape of the seafloor dominate. A body may slide down a chute, pause on a small ledge, shift during a later tremor, and then go again. It may become lodged behind a block in a quiet eddy where scavengers find it quickly. It may ride a small slump and end up under fresh sediment, where only parts are exposed. There is no universal script. The exact trench, the specific gully, and the recent history of slides and quakes matter more than the headline depth number. Equipment makes the difference between a close call and a loss when it comes to mechanical hazards. But equipment has limits. Drop weights are designed to pull a stuck vehicle free by making it buoyant enough to rise. Yet, drop weights themselves can jam if mud and grit lodge in the release mechanism. Acoustic releases sometimes fail when batteries are low or when biofouling coats sensors. And although biofouling is slower in the cold deep sea than in warm shallows, it still occurs over months. Thrusters can ingest fibrous mats from seep sites and stall. Cameras need wipers or fluid jets to clean lenses once silt settles on them, and those systems rely on small pumps that can clog. Each small failure narrows options and makes later choices more brittle. Crews plan around that by testing everything before a dive and by carrying redundancy where weight and space allow. But redundancy is never infinite, especially inside an already heavy pressure sphere. It is also worth noting that not all trenches look or behave the same from end to end. Some segments are fed by nearby rivers and continental shelves and therefore build up sediment quickly. Others sit in the open ocean under waters that are poor in particles, so they accumulate sediment slowly and expose more rock. Where seamounts are being dragged into a trench, the floor and walls can be jumbled by the collision, with chaotic blocks and fresh fractures that catch lines and divert flows in ways that good maps only partly predict. A segment with frequent small slides may be safer to operate in than one that has been quiet for years, because quiet can mean stress has been building. That is not superstition. It is a cautious reading of how systems release energy. For the question at the center of all this, which is what happens to a person or their remains in such a place, the geology answers that the trench is not a quiet tomb, but a conveyor. Steep slopes move things. Faults break and reorganize the bottom. Sediment flows bury and then uncover. Narrow sections channel, wide sections trap. Even the same spot can play different roles through time. In one month it might act like a terrace where scavengers gather. In the next, a slide adds a fresh blanket and resets the clock. Because these processes are mechanical and physical, not just biological, they happen regardless of who or what is present. What keeps this discussion grounded is that we know these behaviors not only from theory, but from evidence that includes long cables broken in sequence by passing flows, lander footage of sudden brownouts followed by smooth new beds, and repeat surveys showing fresh scarps and rearranged blocks where the map used to be neat. Put together, it means that the risks in trenches stem as much from the Earth's motion as from the ocean's pressure. Anyone working there respects both, and anything that arrives there, whether carried by a tether, enclosed in a sphere, or sinking on its own, enters an active slope system that decides the path and the resting place. Given that the seafloor in trench country is not a calm landing pad but a set of moving slopes. The next piece to add is how basic physics decides whether something actually makes it all the way to the axis or stops somewhere along the way. It comes down to buoyancy, drag, and what the object is attached to. Those sound like neat textbook words, but they show up in very practical ways the moment anything starts sinking. The ocean does not carry things straight down by default. It negotiates with the shape, the amount of trapped gas, the weight of gear, and the layout of the terrain it is falling past. Buoyancy is simply the upward push from water that acts on a body because it takes up space. If the upward push is less than the weight, the body sinks. If it is more, the body floats. Humans are close to neutral in seawater because tissues are mostly water themselves, so small details matter a lot. The biggest detail is air. Lungs full of air make a person floaty near the surface. Once that air leaves and water fills spaces in clothing and gear, buoyancy drops and sinking becomes the default. Even then, it is a marginal sink rather than a plunge, and that is why drag, the resistance of water to motion, matters so much. At the very start, clothing and equipment can trap pockets of air. A dry suit or a thick wetsuit is buoyant at the surface because of the gas in the suit material and any air inside. A life jacket uses foam with lots of little sealed bubbles, the same idea. Those bubbles are not strong enough to stay the same as pressure increases. The deeper you go, the more the outside pressure compresses any gas volume. That includes gas inside suit material, air in the lungs, and air under clothing. Within the first few tens of meters, most of that buoyant boost has shrunk a lot. A life jacket meant for boating works beautifully near the surface, but would lose most of its lift as depth increases. Specialized float materials used on deep vehicles are engineered to resist compression, but ordinary foam is not. That difference is one reason why surface gear does not tell you much about what happens hundreds or thousands of meters down. As pressure squeezes gas smaller, water sneaks into places that were airy before. Lungs deflate as air escapes. Fabric and hair, which hold tiny bubbles, give them up. Even gear with trapped volumes tends to vent or fill as seals fail. At that point, the shape of the whole package and the weight of anything attached take over. A person in heavy boots, with a weight belt, and with a steel tank clipped on, will sink more decisively than a person in a thin suit with no extra mass. The tank itself may start positively buoyant when full and swing negative as gas is consumed. But in a sinking scenario without breathing, what matters is its basic material. Steel drops, aluminum can be close to neutral, but either adds to the drag that slows descent. Drag is the quiet actor in this story. Water is thick compared to air, and it resists fast movement by pushing back hard on anything trying to fall through it. Picture the difference between dropping a stone and a crumpled scarf. The stone reaches the bottom quickly. The scarf tumbles and flutters for a long time. Bodies are closer to scarves than to stones when it comes to water. Outstretched arms, loose clothing, and dangling equipment all increase the surface area the water can push against. As speed builds, drag builds faster until it balances the pull of gravity, and then you fall at a steady rate called terminal velocity. In water, terminal velocity for a human without weights is not dramatic. It is fast enough to move you down through the water column in minutes to hours, but it is slow enough that sideways pushes from currents can make real detours. Those sideways pushes are not just near the surface. Internal waves and persistent currents exist throughout the water column. They are slower than surface waves, but much larger in scale. A descending body can drift hundreds of meters sideways before reaching a slope, especially if it is wearing bulky gear that increases drag. Once you get near a wall, gravity takes charge again. The path follows the steepest descent, slipping down chutes, snagging on ledges, and often stopping temporarily on terraces. Those benches act like shelves that catch things coming down. Unless a later event shakes them loose, many objects never pass beyond those shelves. Another factor people expect to matter a lot is decomposition gas. In warm, shallow water, bacteria inside a body produce gases that swell tissues and can make a body float again after 1 or 2 days. In the deep ocean, 2 things blunt that process. The first is temperature. Cold water slows the metabolism of microbes, which means gas is produced slowly. The second is pressure. At depth, gases dissolve into surrounding fluids more readily. A simple way to say it is that high pressure pushes gas molecules into solution. Even if gases form, their volume is much smaller under load, and small bubbles are likely to disappear into tissue fluids and the surrounding water. The usual surface story of a body refloating after a few days simply does not apply once you pass into cold, high-pressure surroundings. Add in the fact that scavengers remove soft tissue, breaking up sealed spaces, and there is even less chance for gas to accumulate. Body composition changes the picture a little, but not as much as people think. Fat is slightly less dense than water, and muscle is slightly more. The variation across individuals is small compared with the effect of clothing, gear, and posture. A compact, tightly wrapped shape sinks more decisively than a spread-out one. Heavy boots and tool belts pull down strongly. A backpack full of tools is an anchor. Cutting away weights changes outcomes quickly because it shifts that fine buoyancy balance. This is why divers practice dropping weight systems in emergencies. The same physics applies to remains. A cut tether or shed belt can turn a slow descent into a slow rise if near the surface, but once you are in deep cold water, the buoyant swing back is unlikely. Gear attachments and tethers are the big deciders when it comes to reaching a trench axis. A person who is clipped to a heavy object that is denser than seawater is much more likely to travel downslope with that object until both find a resting place. If that object is streamlined, it will move faster and farther before drag balances gravity. If it is broad and snag-prone, it will catch on the first ledge it meets. A submersible that fails and breaks open scatters pieces with very different sink behaviors. Bits of metal plunge quickly. Pieces of syntactic foam are buoyant and head back toward the surface if they survive compression. Personal items flutter and drift, and can end up far from the initial site. In those cases, the odds of remains reaching the axis are low because the debris field is wide and because the slopes trap material over a range of depths. The water column adds its own sorting. At some depths, especially where the oxygen minimum zone sits, density layers can slow vertical motion a little. That is not a barrier, but it is another nudge that lets lateral drift grow. Near slopes, there is often a boundary layer where water speed drops close to the wall, then increases a short distance away. A sinking object can enter that thin, slow band, slide, and then drop into a faster ribbon and be pushed sideways again. These details are hard to predict in real time. They show up in the patterns that search teams reconstruct later by combining what they know about circulation with what they find on sonar scans. If a person dies inside a vehicle that stays intact and later returns to the surface or is recovered, the story is straightforward in terms of location. If the vehicle is lost and fails at depth, it sets up the fragment spread mentioned earlier. That is why investigators sometimes find separated fields of debris rather than a single crater. The larger and denser the part, the more likely it is to continue downslope into a trench if it is close to one. The smaller and lighter, the easier it is for bottom currents to push it into side pockets or leave it high on a terrace. Remains can be caught up in that spreading, so even defined trench axes often hold little from a single event. There are scenarios where the path to the axis is more straightforward. In narrow, steep-sided trenches, gravity funnels debris toward the center. If the inner walls are smooth enough and terraces are small, a heavy, compact object can slide or bounce its way to the bottom ribbon. Currents at that depth are often weak compared with gravity on the slope, so once an object is close, it tends to stay. In broad, sediment-filled trenches with large benches, the opposite is true. Objects strand high and rarely move again unless a slide plucks them. In that sense, whether something reaches the axis is less a question of depth and more a question of shape combined with local geometry. Timeframes are often misunderstood. People imagine that reaching the bottom takes only a few moments. In reality, a human-sized object without additional weight descends slowly enough that an open ocean drop from the surface to several thousand meters can take hours. Add weight and streamline the shape, and the time shrinks, but it still is not instantaneous. That span is long enough for currents to shift, for internal waves to pass, and for small detours to become large offsets. The ocean column has plenty of time to reshape a straight vertical line into a slanted, curved path. Another subtlety is suction once something touches very soft mud. Fine sediments can hold an object loosely at first, then cling as water is squeezed out from underneath. Lifting again requires either a new push downslope or an increase in buoyancy, neither of which exists for an unpowered object. That effect locks pieces in place and increases the chance that they will be buried by the next passing turbidity flow. Trapped near the surface of the sediment, they can be exposed by later small slides, then hidden again, repeating the cycle over years without ever progressing deeper into the trench. Search and recovery teams use these patterns when they plan where to look. They start with the last known position and time, estimate sink rates based on size and possible attachments, and layer on the local circulation they know from previous measurements. The first passes look for larger, denser objects with sonar because those stand out. If nothing appears on the axis, they widen to ledges and side gullies where stranded objects often accumulate. This is not a precise science. It is an informed set of bets that are adjusted as each new clue comes in. The very need for this kind of modeling underscores the main point. The path down is shaped by buoyancy and drag, and the end position is controlled by slope geometry and bottom flows. There is also the common question of whether air pockets in clothing or in the gut could create a late refloat at depth. The short answer is that in cold, high-pressure water, those pockets are either compressed to a tiny fraction of their surface volume or they dissolve away. Any bubble that does form finds itself in a place where the surrounding water can hold a lot of gas without bubbling, and the distance to the surface is so great that rising is slow and leaks and scavenging break the seal long before a full refloat can happen. Near the surface, in temperate or tropical seas, the story is different, but trenches change the rules. All of this can feel like the ocean is playing tricks, but it is only obeying simple physics over long distances and times. A body or an object is almost never a clean sphere of known density. It is a complex shape with parts that catch the flow, with fabrics that trap water, with attachments that swing and snag. The slopes it encounters are not smooth ramps. They are rough with blocks, gouges, and soft patches. The water itself is moving in layers. Put those ingredients together, and the outcome shifts from predictable to contingent. When people wonder about the odds of reaching the axis, the most honest answer is that it is possible but not guaranteed, and it depends more on attachments and local terrain than on body characteristics. A heavy tether to a compact object on a steep, clean slope produces a high chance of reaching the axis. A free, sinking body in bulky gear entering a broad, terrace-filled trench has a low chance. Most outcomes fall somewhere in between, with stops on ledges, slow drift into side pockets, and occasional later movement during a slide or quake. The consequence for understanding final resting places is straightforward. The deepest line of a trench is not a magnet. It is a low point surrounded by complex terrain. Many objects never get there. Some arrive quickly with weight and clean shapes. Others take a wandering route and stop early. Pressure rules life and death at depth, but gravity, drag, and slope geometry decide where remains end up. That is why maps of trenches are as important to these questions as any biological detail, and why the notion of an inevitable sink to the very bottom is more myth than rule. Because the deepest point is not guaranteed to be the final stop, the next practical question is what happens once remains or debris settle wherever gravity and terrain decide. The short version is that trenches are not empty. They are cold, dark, and under enormous pressure, but they host communities that are highly tuned to rare food arriving from above. In many places, the very first responders are scavengers that can smell chemical traces in the water and home in from surprisingly far away. What they do in the first hours and days sets the tempo for everything that follows, and the pattern across Hadal depths is consistency in who shows up and in what order, with regional quirks shaped by how much food the overlying ocean delivers each year. We know this because scientists send down baited cameras and instrumented landers. These rigs hold pieces of fish or squid and simply watch. At depths beyond 6,000 meters, footage routinely shows amphipods arriving within tens of minutes to a few hours. Amphipods are small crustaceans related to sandhoppers, but Hadal species can be big by deep-sea standards, and they travel in dense swarms when there is food. Species like Hirundellea gigas and its relatives dominate many of these scenes. In some trenches, especially in the western Pacific, a few fish also appear. These are Hadal snailfish, pale and soft-bodied, adapted to more than 8,000 meters. They are not sharks or large predators. They are small, nimble, and take bites where they can. Once the first waves arrive, the soft tissues on a carcass can disappear quickly. The exact timing varies with size and access, but the early phase is measured in hours to days, not months. Access matters a lot. If the body is inside clothing or gear, amphipods search for openings. They use natural entry points or small tiers and can enter through cuffs, collars, or seams. From there, they work from the inside out because it is protected and rich. Fish cannot reach inside tight clothing, so they take the exposed surface. If the remains are buried by a thin layer of fresh sediment, that slows fish, but not necessarily the amphipods. Some species dig a few centimeters into soft mud to reach food. A deeper burial, on the order of tens of centimeters or more, puts the package below the reach of most animals and shifts the balance toward microbes, at least until later movement brings it back up. Microbial decomposition does not stop at Hadal pressures. It changes. Cold temperatures of roughly 2 to 4 degrees Celsius slow the enzymes that break down proteins and fats. Many surface-dwelling microbes do poorly down there, but deep-adapted species, often called piezophiles for pressure fun-loving take over. They do the same basic chemistry of decay, just at a different pace and with different end products depending on oxygen levels right at the surface of the remains. The surrounding water is usually oxygenated at depth because it comes from polar regions where surface waters sink and spread as deep currents. That oxygen supports aerobic microbes on exposed surfaces. Inside folds of clothing or within cavities, oxygen can be quickly consumed and not replaced, and those micro-pockets become low oxygen zones. In those spots, a different set of microbes uses alternative chemical pathways. If the local chemistry leans alkaline and the environment is low in oxygen, fats can transform into a waxy substance called adipocere, which slows further decay. That effect is patchy and depends on local fluids and temperatures, so it is not a guarantee. One reason these communities are so effective is that they have evolved under a chronic shortage of food. Particles that fall from surface waters are sparse by the time they reach the deep. Trenches sometimes get a little boost because sloping walls funnel organic matter downward, but the overall picture is still lean. When a large item arrives, whether it is a fish, a squid, a whalebone, or something human-made, the system treats it as a windfall. Chemical plumes of amino acids and other compounds spread down current and across the bottom, and animals follow those gradients like a scent trail. Amphipods can build energy reserves quickly during these pulses. Snailfish cruise the area, picking off larger pieces and the occasional amphipod. Isopods, which are armored crustaceans, show up in some trenches as well and take slower, methodical bites. Soft tissue removal by animals often outpaces microbial rot in the first stretch of time. Cold water gives that advantage to scavengers. A simple way to understand it is that a mouth, even a small one, removes large chunks quickly compared with bacteria that must digest protein molecule by molecule. Once the protein-rich and fatty tissues are gone, what remains are tougher elements like cartilage, tendons, and skin that can be slower to chew and slower to break down. In that intermediate window, days to weeks, a skeleton with some connective tissue can persist, especially if burial or protective clothing limits access. Bones are a longer story. The mineral in bone is mostly apatite, a phosphate mineral that dissolves slowly at deep ocean pH. Biological activity is the main driver of bone loss, not chemistry. That is where bone-eating worms known as Osedax come in. They are specialized animals that colonize bones, extending root-like structures into the mineral to reach the fats inside. They host bacteria that help them perform this digestion. Osedax species have been documented on bones recovered from thousands of meters, and they can establish colonies within months if conditions allow. In trenches, where temperatures are low and burial can be intermittent, bones can persist for months to years, with Osedax and small invertebrates progressively reducing them. The exact timeline depends on exposure. If sediments cover bones quickly and keep them anoxic, colonization by Osedax slows. If bones sit on the surface in oxygenated water with active scavenger traffic, colonization and erosion proceed faster. Food supply from the surface sets a lot of this variation. Trenches beneath nutrient-rich regions like those down current of productive shelves or upwelling systems tend to host denser scavenger populations. Amphipod swarms arrive faster and are thicker, and a carcass disappears quicker. Trenches under ocean gyres, where surface productivity is low, still have scavengers, but fewer. Consumption is slower, and microbial steps take a larger share of the work after the initial feeding. The South Sandwich region in the Southern Ocean is an example where cold conditions are extreme and seasonal blooms influence food input. Amphipods remain active and do the initial cleanup, but microbial processes between events are slow. By contrast, trenches like parts of Java or those near river outflows sometimes see richer benthic communities because more organic material arrives overall. Pressure also shapes who can live there. Fishes have a practical depth limit set by the chemistry of their cells. To keep proteins working under pressure, many deep fishes increase compounds like trimethylamine N-oxide, which stabilize proteins. But that strategy has a limit because making more of these molecules changes the cell's water balance. Somewhere beyond a bit more than 8,000 meters, fishes struggle to maintain function. That is why Hadal fish records cluster around a little over 8,000 meters. Beyond that, communities are dominated by invertebrates like amphipods, isopods, holothurians, and polychaetes. Holothurians, the sea cucumbers, are especially common on Hadal floors where they process sediment, digest organic particles, and rework the surface. They are not predators in this context, but their movement stirs the top layer and can bury or expose small items like loose bones over time. Another pattern that shows up in lander footage is how feeding attracts a web of participants. Small foraminifera, which are single-celled shelled organisms, increase around rich patches as they consume bacteria. Microbial mats can develop on exposed fatty areas, changing the microchemistry and attracting grazers that are not strictly scavengers. This secondary wave is subtle and slow compared with the amphipod rush, but it still matters over weeks to months by shifting which microbes dominate and by altering whether certain tissues persist. If a seep is nearby, the chemical background changes again. Methane and sulfide can favor sulfate-reducing bacteria in micro-pockets under remains, softening tissues in place and sometimes generating mineral crusts that briefly outline where soft tissue used to be before they crumble. Clothing adds practical complications. Fabrics slow animal access and create low-oxygen alcoves that alter decay chemistry. Zippers, seams, and elastic bands create pinch points where amphipods pile up. Glove and boot interfaces become entry paths. Once scavengers are inside, they strip tissue efficiently, leaving skin and outer layers relatively intact until they decay on their own or tear under their own weight. Heavy gear attached to a belt or harness can keep a torso pinned. When a turbidity flow passes, pinned parts are more likely to be buried in place. Later, a slide or current can uncover parts selectively. That is how you end up with scattered bones exposed, while other elements are still buried a few centimeters away. Scavenger behavior also changes with light and flow, even in total darkness. Many amphipods are sensitive to vibrations and prefer to feed in slightly calmer periods. If a lander drops and stirs the bottom, there can be a short delay before the swarm returns to full density. Snailfish are cautious around thrusters and lights. They dip in and out, testing. In quieter, unlit scenes, their visits appear more relaxed and they take larger bites. Sound, which carries very well at depth, can startle animals temporarily if a vehicle pings too loudly or a new acoustic source begins. These are short-lived effects, but they remind you that the community is alert and responsive, not numb. Over longer spans, burial and exposure cycles driven by geology intersect with this biology. After an initial feeding, a thin blanket from a small slide might hide what is left for weeks. Amphipods disappear from the camera's view because access is gone, though some keep tunneling at the edges. If another slump tears the new layer away, feeding resumes from where it paused. Each cycle gives microbes a little uninterrupted time in an oxygen-limited situation, then brings animals back in. Because trenches are active, these cycles are common and they stretch the total time remains persist without preserving them in a pristine state. Instead, the picture is one of intermittent progress toward skeletonization and dispersal, with the timeline punctuated by physical events rather than set by a simple decay curve. People sometimes wonder about disease and whether cold, deep waters preserve pathogens. In practical terms, human pathogens are not adapted to the cold, pressure, and salinity at depth. They do not compete well with native microbes, and they do not drive the decomposition story. The risks and processes are ecological, not medical. Forensics underwater cares more about access, temperature, and scavenger density than about any specific microbe that was present before immersion. It is also useful to calibrate expectations about visibility and detectability. Once soft tissue is gone, bones are pale and stand out on mud. Cameras and sonars can spot them from a distance in clear water. In turbid settings or where dark manganese coatings develop on exposed surfaces over time, bones blend in more. Small bones vanish first in this visual sense, either buried by animal movement and light sediment drift or carried a short distance by currents once they are detached. Larger, long bones stand out longer. Teeth and dental restorations can last longest of all because they are hard and compact, but they are also easy to miss unless you are close. Regional differences give this whole picture local flavor. In the Mariana system, amphipod density at Bates is high, and snailfish attendance at more than 8,000 meters is now well documented. In the Tonga and Kermadec regions, similar patterns hold with variations in which amphipod species are most numerous. The Puerto Rico Trench, while shallower, sits near busy shelf edges that can supply pulses of organic matter, and so scavenger response is brisk when food arrives. The South Sandwich Trench is exceptionally cold, and the pace of microbial steps is slow, yet amphipods stay efficient, likely because they are adapted to those temperatures. The Java Trench sits beside tropical shelves and river inputs, and lander work there often records heavy scavenger loads that can strip bait quickly. Across all these places, the same basic sequence plays out. Animals take the lead, microbes follow, and bones finish the story over months to years with help from specialized worms and small invertebrates. If you step back, the everyday reality in Hadal ecosystems is steadiness punctuated by windfalls. Most of the time, these animals sift thin organic rain, graze microfilms, and wait. When a large food item appears, they switch to fast action. That switch is why remains do not sit untouched for long, even at depths where light never reaches and temperatures hover just above freezing. The impression of stillness is misleading. Motion is there in the form of chemical plumes, small feet and fins, and a long list of tiny decisions by animals that have learned to move quickly when opportunity arrives. All of this means that preservation at trench depths is not the rule. Cold and pressure slow some processes, they do not freeze the scene. Scavengers down there are effective, tuned by scarcity, and fast enough to change the picture in hours and days. Microbes are patient and finish what animals start. Bones hold out the longest, held up or held back by physical burial and by the pace of colonization from worms and other small specialists. Which trench you are in, how much food it usually gets, and whether the spot is on a terrace or down in a narrow axis all tilt the details one way or another, but the overall sequence holds. Remains are treated like any other rare food fall in the deep sea, and the community does not hesitate to use them. All that busy feeding happens inside water with its own chemical quirks, and those quirks matter because they can speed things up, slow them down, or change what exactly gets left behind. The trenches sit in deep, cold, oxygenated water for the most part, but patches along their margins leak unusual fluids, and even a small patch can flip the script in the space of a few meters. So it makes sense to talk about the chemistry you actually meet down there, not in an abstract way, but in terms of how it nudges decomposition, bone survival, and whether anything gets a brief chance at preservation before the next slide or swarm resets the scene. Start with cold seeps because they show up all along subduction margins. A cold seep is not hot like a vent. It is simply a place where fluids rich in methane and sometimes hydrogen sulfide seep out of the seafloor. Those molecules are food for microbes. They build whole communities that do not rely on sunlight at all, using chemical energy instead. You often see clams and mussels in these spots because they host bacteria in their tissues that use those seep chemicals. Around the clams there are mats of white or yellowish filamentous bacteria, and the sediment smells of sulfide if you disturb it, the same rotten egg smell you get near a sulfur spring. That is for context. For a body or any chunk of organic matter, a seep changes which microbes show up first and how fast certain tissues break down. Hydrogen sulfide in particular has a strong effect because it indicates that oxygen is scarce in the sediment and because it supports bacteria that use sulfate to decompose organic material. Those bacteria work without oxygen, and their waste products can be corrosive to some metals and can stain soft tissue. If remains land right on a seep patch, aerobic microbes that need oxygen are pushed aside and anaerobic ones take over. Amphipods are fine with low oxygen and they usually keep feeding anyway, but fish are more cautious in strong plumes. If the exposure is patchy, you can end up with one side of a body processed mostly by animals and the other side stewing under a sulfide-rich smear that favors bacterial softening. That split can be confusing when people try to read the timeline later because it makes one part look older than another. Methane alone is not toxic the way hydrogen sulfide is, but it shapes the habitat by feeding methane-oxidizing bacteria. Those microbes can make sticky films, and in the right pressure and temperature window, methane can crystallize with water into methane hydrate, which is an ice-like solid. At Hadal pressures and cold temperatures, hydrates are stable in sediments where methane is abundant. If a seep is vigorous, hydrate can occur just under the surface. That does not preserve remains like a freezer would, but it can trap things in place. A limb or a strap pressed into that layer can get cemented temporarily, changing how easily animals can drag pieces around and how quickly a turbidity flow might dislodge them later. If seep flow wanes and the hydrate dissolves, that grip loosens and buried bits can shift again. pH, the measure of acidity or alkalinity, is another lever trenches can pull. Most deep seawater sits slightly on the alkaline side of neutral. That number moves slowly, but it is not the same everywhere. Inside certain forearc regions where serpentinite rocks interact with water, the fluids that rise can have very high pH, even into the low teens, which means strongly alkaline. That sort of fluid has been documented in a few places along the western Pacific forearc. When an alkaline seep mixes with surrounding seawater, it creates a patch where fats can be chemically altered more readily. Saponification is the word for turning fat into a soap-like substance, and adipocere is the waxy result when that happens inside soft tissue. In shallow, cooler, and low oxygen conditions on land, adipocere can form and slow decomposition. In the deep sea, cold temperatures already slow many reactions, but the oxygenated water usually keeps adipocere from becoming widespread. In an alkaline, low-oxygen pocket inside clothing, though, the balance can tip, and small patches of adipocere can appear. It is not a guarantee or a blanket preservation strategy. It is a local quirk that can make a section of tissue waxy and more resistant to immediate decay. On the flip side, mildly acidic microenvironments can form inside decaying remains because carbon dioxide from microbial respiration dissolves and lowers pH locally. That can soften collagen and encourage faster breakdown of connective tissues. None of these pH effects run the show by themselves. but they are the kind of small edge differences that over weeks change whether skin sloughs in sheets or frays, whether fatty deposits become waxy or leach away, and whether tendons hold joints together a little longer or give up quickly. Deep water chemistry also sets expectations for bone. People often hear that deep waters are undersaturated with respect to calcium carbonate and assume bones will dissolve fast. The key detail is that bone mineral is mostly apatite, a calcium phosphate, not calcium carbonate. Apatite dissolves slowly in seawater at the temperatures and pH you find at depth. So, chemistry alone is usually not the main enemy of bone. Biology is. Bone-eating worms like Osedax and a suite of small invertebrates and microbes are the ones that erode holes, strip marrow lipids, and gradually weaken the structure. That said, chemistry is not absent from the story. In low oxygen, sulfide-rich conditions, iron in sediments reacts with sulfide to form pyrite, and bones can pick up dark mineral coatings. In other places, phosphate can reprecipitate as new minerals like vivianite under reducing conditions, forming blue-gray crusts in fresh sediments. These mineral coatings sometimes slow erosion by animals for a while, but they can also make bones more brittle. The net effect is variable and very local. Metals add another layer. Trenches sit next to volcanic arcs, and even if the big hydrothermal action is on ridges or in back arc basins, fine particles rich in iron and manganese can still reach trench slopes. Over time, those oxides form thin black or brown films on surfaces, including bones, clothing, and metals. The coating is not thick armor, but it does change the look and the microhabitat. Bacteria that like to use manganese or iron can colonize those patches, and the slightly roughened surface can trap more silt. For remains, this mostly means a gradual darkening and a bit of extra sediment clinging to textures, which can hide small bones unless you are close with a camera. Oxygen is the quiet baseline that many of these processes ride on. The deep waters that fill trenches usually come from high-latitude regions where cold, oxygen-rich surface water sinks and spreads. That means the water just above the seafloor can carry plenty of oxygen, but the sediment itself flips to low oxygen very quickly, often within millimeters. Microbes on exposed surfaces use up oxygen first, and then as you go a few millimeters down, you hit layers where nitrate, then sulfate take over as the chemicals that accept electrons in microbial metabolism. That sequence is what produces hydrogen sulfide and methane in the first place. So if remains sit on the surface and get good flow, aerobic processes and animal feeding dominate. If they are draped in fabric, tucked in a hollow, or dusted by fresh, fine sediment, the microenvironment becomes low oxygen and sulfate reducers step in, bringing sulfide chemistry into play, even if the larger background water is fully oxygenated. Clothing and gear make that microscale patchiness stronger. A zipped jacket, a hood, gloves, and boots all create creases and pockets that slow water exchange. Inside those pockets, carbon dioxide rises, pH dips, and oxygen drops, which favors different microbes than the exposed outer surfaces. If the spot is near a seep or in a naturally alkaline patch, the pH can swing the other way. Either way, you end up with adjacent areas a few centimeters apart that are on different chemical trajectories. That is why the same set of remains can show brown sulfide staining in one section, a waxy fat deposit in another, and a cleanly scavenged bone elsewhere. The rate at which soft material disappears also depends on how these chemistries interact with animals. Amphipods do not mind low oxygen so much, but they do avoid strong sulfide zones if better food is nearby because bacteria-covered surfaces are not easy to handle, and sulfide can be directly toxic at high levels. Snailfish follow their prey and take advantage of open access. If chemistry blocks access, animals switch to what is available, and microbes get more time. If a turbidity flow lays down a few centimeters of new mud, the oxygen barrier can lock in quickly, halting animal feeding even as bacteria continue to work in the dark. There is a fair question about whether any of these chemical patches actually preserve things for long. The honest answer is that they buy time rather than deliver long-term preservation. Adipocere, when it forms, slows microbial progress in that spot, but it does not halt it forever. Mineral crusts can shield bone for a while, but they are fragile and often break during the next disturbance. Hydrate cement can hold things until seep flow changes. All of these are interruptions in the general march toward skeletonization and dispersal, not permanent stops. The deep sea is just too active biologically and mechanically for chemistry alone to keep a whole body intact for very long. Patchiness is the word researchers use a lot, and it is not hand-waving. Lander studies and submersible dives show abrupt changes over distances you could cover in a few paces if you were on land. 1 square meter can be ordinary gray mud. The next can be a thin white microbial mat with a whiff of sulfide, and a few meters away you can find bubbly sediment with methane ebullition. Put remains across that gradient and you get mixed signals. That is why interpretations drawn from a single video frame or a single grab sample need caution. The same trench can host high pH serpentinite-influenced seeps in one valley and relatively normal deep water chemistry on the next ridge. Time adds another layer because seep flow is not constant. It pulses with tides, with distant storms, and with the slow breathing of the subduction system itself. Materials that come down with a person bring their own chemistry. Neoprene, nylon, metals, and adhesives all behave differently in cold, oxygenated salt water. Neoprene loses buoyancy as gas bubbles in the foam compress and as the material ages. Nylon can pick up biofilms and stain. Steel rusts, aluminum forms protective oxides, and copper alloys can react with sulfide to make black copper sulfide coatings. None of this changes the big biological processes, but it does contribute to how quickly gear falls apart and how easily animals can penetrate. A zipper clogged with mineral precipitate or fine mud becomes a fixed seam rather than an opening, while a corroded fastener that fails can peel back a barrier and hand scavengers an entry point. Even without seeps, chemical gradients track topography. Depressions collect fine organic particles and can go low oxygen quickly. Raised ridges stay flushed with oxygenated water. On a terrace where bottom currents sweep regularly, exposed bones clean faster and pick up manganese oxide stains more quickly. In a sheltered gully, soft tissues last longer under thin sediment caps and smell of sulfide when disturbed. Those are quiet differences with steady consequences. They do not announce themselves loudly, but they add up. It also helps to keep in mind where chemistry definitely is not the main driver. Hydrothermal vent-style mineralization, the bright orange and black chimneys people picture, is largely a mid-ocean ridge and back arc feature, not a trench axis feature. Traces of volcanic metals can dust trench slopes, but you are not going to see a body in a trench get flash-plated in copper or entombed in silica. The chemical influences that matter here are the subtle ones: pH drift from alkaline fluids, low oxygen pockets that encourage sulfide, and the general deep-sea tendency toward carbonate undersaturation that touches shells more than bones. The biology still leads, using whatever chemistry sets the table. From a practical perspective, scientists and search teams lean on chemistry as a clue. Sensors that detect methane or oxygen dips help map seep patches. pH probes confirm alkaline spots. Sulfide sniffers warn of zones where a camera may fog with precipitate if disturbed. Knowing where those are helps you predict where remains might decay differently and where a later camera survey might find bones with dark coatings or waxy residues. It is not a perfect guide, but it narrows options and prevents surprises like a sudden cloud of white carbonate particles blooming into view when alkaline seep fluid mixes with seawater at a disturbed spot. Stepping back, the chemistry of trenches is not a single blanket. It is a pattern woven into the terrain. Cold seeps bring methane and hydrogen sulfide that reorganize microbial priorities and deter some animals. Serpentinization in parts of some forarcs lifts pH to unusual levels that can tip small pockets of tissue towards saponification. Deep water itself stays cold, slightly alkaline, and poor in calcium carbonate, which means shells and corals struggle, but bone mineral is relatively safe from simple dissolution. Metals accumulate slowly as thin films, darkening surfaces and inviting new microbial players. All of this is happening in a place where a nearby slide or a quiet uplift in seep flow can redraw the map by the time a second visit is possible. So when you think about what chemistry does to a body in a trench, think in terms of nudges, not absolutes. Chemistry pushes different microbes to the front, encourages or discourages animals at the margins, and sometimes coats or alters tissues in ways that buy a little time. It does not erase the roles of amphipods, snailfish, worms, and gravity. It works alongside them, meter by meter, moment by moment, producing that uneven, locally specific outcome that is so common in the deep sea. In one small area, a bone might darken and thin under Osedax while picking up a manganese sheen. A short distance away, a fatty patch might turn waxy under a flap of clothing bathed in alkaline seep fluid. And just as those differences settle in, a fresh drift of sediment can cover everything, stop animal traffic, and hand the tools back to microbes until the next event turns the page again. Those local chemical quirks only matter if a vehicle can actually get there and work safely, and that depends on machines that hold a tiny bubble of surface conditions against everything outside trying to squeeze it flat. Pressure is the one rule that never changes at Hadal depth, so all the engineering starts with that number in mind and then builds outward to power, life support, navigation, and recovery. The gear looks sleek in photos, but the truth is it is a collection of careful compromises, lots of redundancy where it counts, and a constant awareness that a narrow safety margin gets narrower as you go deeper. The shape that wins under compression is a sphere or something very close to it, because a sphere spreads load evenly. That is why crude submersibles built for Hadal work put people inside thick metal spheres. Titanium alloys are common because they combine high strength with good resistance to corrosion and cracking in salt water. High-strength steels can work too, but they are heavier and need more attention to corrosion and hydrogen effects. No matter the metal, every weld, bolt hole, and interface is a place engineers treat with suspicion. Before anyone rides inside, a new hull is proof-tested in a pressure chamber to pressures beyond the intended operating depth, and then inspected with tools that can see tiny flaws like ultrasound, dye penetrance, or X-ray pictures. Those checks do not make a hull immortal. They simply reduce the chance that a small imperfection will grow into a crack under repeated dives. Viewports are the other items that make people nervous, and for good reason. A window in a pressure sphere is a hole in the strongest shape. Designers keep them small, thick, and shaped so the outside pressure pushes them more tightly into their seats. Materials vary with depth rating. Clear plastics like acrylic do well at moderate depths, but they creep over time. For greater depths, thick glass or quartz, sometimes sapphire, is used because it handles compression better and ages more predictably. The trade-off is visibility. You get tiny portholes rather than panoramic views. Most seeing at Hadal depth is done with external cameras and lights, with small windows reserved for close work or psychological comfort. Inside the sphere, the job is simple to describe and fiddly to execute. Keep the air breathable, the temperature tolerable, and the crew aware of the outside. Oxygen comes from tanks or generators. Carbon dioxide is scrubbed with chemical canisters filled with soda lime or lithium hydroxide, and humidity is managed to prevent condensation that can fog instruments or turn the inside slippery. The scrubbing process makes heat and water, so fans and filters run constantly, and there are backups for each component. Carbon dioxide rise is sneaky because the first symptoms are headache, confusion, and air hunger, which look like stress. That is why real-time gas monitors are non-negotiable and why procedures call for swapping scrubbers early rather than squeezing out extra minutes. When you are days from a port and many hours below the surface, you do not get to wing it on life support. Power is the next constraint. Batteries supply everything from thrusters to lights and life support. Lithium-ion cells dominate because of their energy density, which simply means you get a lot of power for the weight and space. At depth, those batteries are often placed in oil-filled, pressure-balanced housings outside the crew sphere so that the hull is not sharing space with a fire risk. Oil-filled means the casing flexes and the oil takes the pressure load, keeping the internal cells at near ambient pressure. Cabling then runs through pressure-rated connectors into the sphere. If designers put batteries inside instead, they need robust containment and fire suppression that works in a small, closed room. In both layouts, the battery packs are divided into independent banks so that a failure in one does not take down the whole vehicle. Energy budgeting is conservative. Pilots track watts, consume the way sailors track fuel because any surprise on the way up is a bad surprise. Moving a heavy sphere through water calls for thrusters, and those thrusters have to be pressure tolerant or pressure compensated. Electric motors usually sit in oil-filled housings with flexible bladders, so outside pressure does not crush seals. Bearings and shafts use materials that do not gall under load and that tolerate a little grit, because even small sediment clouds can get everywhere. Thruster failures are not rare in deep work. A motor that ingests silt or a connector that wicks water can die quietly. Vehicles are designed to tolerate losing one or more thrusters and still maintain basic control. If power is gone altogether, the last line of defense is ballast that can be dropped to trigger a passive ascent. Those drop weights are heavy blocks held by mechanisms that release when commanded or when a fuse wire burns or when a corroding link finally parts. A good design releases weights if power is lost for long enough, so that a dead vehicle becomes a rising vehicle rather than a permanent resident. Buoyancy foam is another deep-sea staple. Syntactic foam, to use the shop term, is a solid made by embedding many tiny hollow glass or ceramic spheres in resin. The hollow spheres resist crushing, so the whole block stays buoyant even under great pressure. Designers use foam blocks to tune a vehicle's natural tendency so that with weights attached, it is slightly heavy, and with weights dropped, it is comfortably light. Ordinary foams used in life jackets compress and lose lift quickly as depth increases. That is why you find syntactic foam on every deep craft that is meant to return. Communications and navigation at depth lean on acoustics because radio waves do not travel well through seawater. Short baseline or long baseline acoustic systems measure time delays between a ping sent by the vehicle and replies from seabed beacons to estimate position. In trenches, echoes off steep walls can confuse these systems, so pilots cross-check with depth readings, Doppler logs that sense speed over ground with sound, and maps made in advance. Bandwidth is thin. You cannot live stream high-definition video through water, You can send short status packets and receive commands. That limitation shapes how failures are handled. The pilot is not waiting for someone topside to tell them what to do in the next few seconds. Most of the critical actions are local and rehearsed. Launch and recovery are points of real risk. You move a heavy, delicate vehicle through waves with cranes and winches, and a misstep can swing it into the hull of a ship or dunk it so that hatches go under unexpectedly. Good teams wait for the right sea state and use taglines and trained deck crews. Umbilicals used by remotely operated vehicles add another layer of hazard. A long tether can snag on a ship's structure during launch or on the seafloor during the dive. Tethers have weak links that break before they yank a vehicle into trouble, and cutters that can sever lines below if a snag becomes impossible to clear. None of that is elegant, but it is practical. The sea does not care why the line is stuck. Failure modes are simple to list and complicated in practice. Slow leaks through seals and connectors are common. A single drop per second can add up over hours and create puddles in places where electronics live. Designers pot sensitive circuits in resin or immerse whole modules in oil to keep water away. Acoustic transponders that are meant to help you find the craft again can fail if their batteries go flat or if they are buried by a slide. Engineers mitigate by carrying more than one beacon and mounting them in separate places. Mechanical joints on suits and vehicles, the places where motion has to happen, demand constant maintenance. O-rings are cheap, but the grooves they sit in must be perfect, and a hair or a grain of grit can make a good seal into a slow leak. Catastrophic failures are rare, but they are the ones that set the tone of caution. A pressure hull failure at Hadal depth is not something you ride out. It ends the moment it begins. That fact shapes design culture. The hull is not a place for experimental materials without a long track record in compression. Metals with known behavior under cycling and with well-understood crack growth rates are preferred. Composites shine in tension but can be unpredictable in external compression if not designed and tested with extreme care. Engineers also worry about fatigue, which is the slow growth of microscopic cracks as a structure sees stress again and again. Each dive adds one cycle. That is why you keep a dive log for the hull, perform periodic non-destructive inspections, and retire parts on schedule even if they look fine. Heat and fire in a small cabin are high on the list of non-pressure hazards. A shorted cable or a faulty charger can start smoke, and smoke spreads instantly in a sealed space. Crews carry masks and small scrubbers, and they practice isolating power quickly. You cannot just open a window to clear the air. Oxygen levels are kept modest to reduce fire risk, which limits how quickly a flame can grow. Still, the best fire is the one prevented by design, separating battery spaces, using fuses that cut power fast, and routing cables so they cannot chafe. Entanglement is a classic trench risk. The walls are steep, cut by gullies and scattered with boulders. A manipulator arm can slide behind a rock, a cable can settle into a notch, or a dropped tool can lodge where you cannot see it. Vehicles carry cutting tools and have procedures for backing out the way they came in, rather than forcing a new path. The safest practice is to keep the vehicle a few meters off the wall and extend tools the last bit, rather than tucking the whole craft into a slot. But sampling and inspection sometimes demand bold approaches. Good piloting is measured by how boring it looks on video, not by how close the camera gets to dramatic scenery. Classification and certification sound dry, but they are anchors. Independent bodies set rules for how pressure vessels should be designed, tested, and operated. They inspect drawings and hardware, witness tests, and issue certificates that say a craft is safe to a certain depth with a certain margin. Those documents do not remove risk and they do not replace judgment, but they force discipline. If a change is made, it has to be evaluated and documented. That slows things down, which is exactly the point when the frontier feels exciting and shortcuts tempt teams to move faster than they should. Not every deep mission is crewed. Remotely operated vehicles and autonomous systems do much of the work in trenches precisely because they carry no one inside. They can take on higher risk profiles, get closer to slopes, and accept a greater chance of loss. Even then, budgets and schedules matter, and repeated losses shut down programs. The same physics that punishes crewed craft punishes robots: pressure, cold, abrasion, and remoteness. Engineers protect uncrewed vehicles with many of the same tools: oil compensation, syntactic foam, drop weights, multiple beacons, and conservative power budgets. Human factors round out the picture. Crews are trained to hear and feel their vehicles. A new groan from a joint, a vibration in a thruster, an odd response from ballast, or a carbon dioxide reading that creeps up rather than holding steady are all reasons to pause and reassess. The hardest calls are the ones that end a dive early for signs that are not definitive. The culture that keeps people safe rewards turning back as a success, not a failure. That attitude is not drama. It is a rational response to the distance and time involved. If something escalates at 8,000 meters, no helicopter is coming. Your only rescue is the equipment you brought and the discipline to use it well. Search and recovery procedures are baked in before a mission starts. Acoustic beacons announce a craft's position. Emergency buoys with thin lines can pop free on command and carry a radio or satellite beacon for when the vehicle surfaces. Strobes mounted outside flash through the night. Topside teams set timers for check-ins and assume failure when contact is lost beyond the expected blackout zones. That schedule gives families and managers honest timelines and keeps everyone from waiting for miracles that the physics does not support. Maintenance after each dive may not look like heroics, but it is where safety lives. O-rings get replaced, housings are opened and dried, connectors are cleaned and greased, fasteners are inspected and torqued properly, and logs are updated with any anomalies. Small parts that seem fine in the shop can misbehave under pressure, so teams prefer components with long histories rather than the latest novelty. When designs do change, the changes are tested in chambers and tanks before they ever see a trench. That patience takes funding and time that are hard to secure, which is another quiet risk for this field. Underfunded teams cut corners even when they do not intend to. The ocean does not grant discounts. The bigger point hiding in all of this detail is that the Hadal Zone does not care which trench you are in. The exact numbers change by a few hundred atmospheres. The topography changes a lot, but the engineering problems repeat. Hold pressure out, keep people breathing, move and see in cold, dark water. Avoid getting stuck. Come back up on your own even if most systems are dead. When designers and crews respect those basics, the dives look boring from the outside and produce the steady science and mapping that make the deep ocean legible. When the basics are rushed or traded for convenience, the penalties are final. So if you picture the equipment that reaches trench depths, think less about sleek exteriors and more about joints that keep oil where it belongs, batteries that sit in their own baths, foam that does not crush, windows that are tiny but honest about their limits, and weights that let go even when no one is left to tell them to. The marvel is not that the machines go so deep. It is that they do it by embracing simplicity wherever possible and by assuming that whatever can fail eventually will. That mindset is what lets a small human space ride safely down through the ocean's heaviest, quietest places and come back with data and stories rather than with drama. That small human space only pays off if the people inside can stay calm and make good calls, and that comes down to what the world feels like minute to minute while you are down there. Inside a Hadal-rated vehicle, the sensory diet is simple and steady. The cabin is dim, lit by instrument panels and a few task lights. Fans hum because life support is always moving air. Pumps click on and off as ballast shifts. Now and then the hull gives a soft creak as outside pressure climbs and the sphere settles microscopically. None of it is alarming if you have heard it before. Most of the time, the outside is just black until you turn on lights, and then it is a tunnel of particles drifting past like slow snow. Bioluminescent flashes streak by when something touches the flow around the hull. That mix of quiet and occasional sparkle sets a tone that is more workroom than adventure. Time stretches on the way down. A descent to Hadal depth is not a sprint. It takes many hours, and the hours are filled with checklists, system readouts, brief updates to the surface when the acoustic link is clear, and small adjustments to keep the vehicle on plan. You feel slight changes in acceleration when ballast tanks vent or fill, but otherwise it is steady. The brain is occupied but not flooded, and that is by design. Crews keep the workload even so that nobody is racing to catch up when the bottom arrives. The routine is familiar. Confirm oxygen production, confirm carbon dioxide scrubbing, check humidity, log power use, verify the position solution, scan sonar, tweak the trim, and repeat. It sounds dull because dull is safe. When you do look outside, the light from the vehicle falls off quickly. At a few meters, it is strong. By a few tens of meters, it is gone. You rely on cameras that can gather faint light and on sonars that paint the surroundings with sound. The sonar chirps are a regular part of the soundscape. You get used to their rhythm, and you notice when it changes. A faster ping can mean a closer look is underway. A slower ping can mean the crew is conserving power, or that the scene is clear and does not need high detail. The water carries sound better than air does, so you hear the thrusters spool up as a smooth push that rolls through the hull rather than as a sharp whine. The body notices the cabin more than it notices the depth. Temperature inside is kept near what you would want in a chilly office. If humidity creeps up, you feel it as a dampness on your skin, and you wipe condensation off a viewport before it fogs completely. If carbon dioxide begins to climb because a scrubber is near the end of its life, the first clues are subtle. Some people get a mild headache, some feel warm or flushed, others feel a growing urge to breathe faster, even though oxygen levels have not changed. Training drills into everyone that feelings are not data. You look at the instrument that reads partial pressure of CO2 and you act on that number. Swap the scrubber, increase circulation, and retest. The habit is to fix it early rather than push for a few more minutes of work. Communication with the support ship is not like talking on a phone. It is short bursts when the link is good. You send a packet with depth, position, heading, and key systems. They reply with acknowledgements and any updates on weather and ship position. If the stars align, you pass short notes about what you are seeing. When the link is bad, you do not wait. You continue on the plan. Losing the link is a stressor for newcomers, but veterans treat it as normal. The plan assumes autonomy. If something goes wrong, the fixes are in the vehicle, not waiting in someone else's mouth. The psychology of the bottom is different from the psychology of the descent. When the seabed comes into view on sonar and then in lights, attention tightens. You go from hours of monitoring to minutes where a lot happens. You gauge altitude precisely. You avoid stirring up the fine sediment because one bad plume can blind cameras for a long time. You pick targets that are safe to approach. In trenches, that means staying off steep walls and never tucking under an overhang. Everyone talks less and says more with fewer words. You hear call and response between pilot and co-pilot. range, altitude, current set, thruster status, power remaining. The rhythm is practiced, which is what keeps stress in check. If an anomaly starts, it often announces itself softly. A thruster takes a second too long to spin up. A ballast valve cycles twice for a single command. A carbon dioxide number drifts upward when it should be flat. Good crews treat these as early warnings. You pause the mission objectives, get the vehicle stable, and troubleshoot. There is no prize for pressing on through a list if the machine is whispering that it needs attention. This is where the knowledge that rescue is not coming helps. It sounds grim, but it focuses the mind. You are not managing for public relations or schedule. You are managing for life support and a clean trip home. Entanglement is a kind of trouble where senses and nerves meet. It starts with a change you can feel through the hull. The vehicle stops moving as expected. Thrusters push and nothing gives. The sonar picture is confusing because a wall is close and the line that snagged you is not visible. Your world switches to a very narrow loop. Back out the way you came, do not make sharp turns, do not add slack to a trapped line, and keep the vehicle a little off the bottom so you do not dig in. The pilot makes small inputs and waits for the result instead of chasing the controls. If the umbilical on a remotely operated system is trapped, the topside team eases tension and moves the ship slowly to change angles. If none of that works, the next rungs are dropping weights, cutting a small portion of line, or abandoning a tool that stuck. Senses are watching instruments, not hunting for drama. The language stays dry. A minute saved by impatience can cost hours if silt rolls up and you lose all reference. Rockfall is rarer, but it is a known risk along steep walls. The sound is distinctive, a series of ticks or a soft rattle. You do not look for the source because you will not see it in time. You pull away from the slope, raise altitude, and wait. Those actions are preset and practiced. The psychology here is avoiding the trap of curiosity. The listening and the moving are practical, not theatrical. You go back to work only when the pings and video confirm clear water and safe distance. Everyone wants to know about fear at depth. The honest answer is that there is less fear than you might expect, and more effort. Apprehension before the dive is normal. It peaks during launch and recovery because the ocean is chaotic at the surface and human error is possible. Once you are inside a stable sphere and the procedures take over, there is comfort in the script. You know the machines, you know the numbers, and you know the exit steps. Even in a problem, most people experience narrow focus rather than panic. The brain ticks through steps the way it was trained. Fear, when it crops up, is a low rumble on the edge of awareness that says, do not waste time and do not take chances. The exception to that controlled experience is hypoxia or carbon dioxide overload, which can hijack how your body feels in a way that tricks your mind. Hypoxia can come from a leak that dilutes oxygen or from a malfunction that stops oxygen addition. You do not feel hypoxia early. Cognition just gets woolly. You might struggle to do simple math or to remember a step, and you might not care as much as you should. That is why oxygen levels are watched constantly and alarms are loud. Carbon dioxide overload feels very different. It produces a strong sense of air hunger and can bring anxiety with no obvious cause. It can also cause a throbbing headache and a sense of warmth. Training teaches you to trust the senses and to follow the fix, even if your instincts are telling you to breathe faster. Slower breathing and good circulation work better than panting in a closed system. Crews practice these corrections until they are automatic, because in the moment, instinct is not your friend. People sometimes ask bluntly what the last moments would be like in the worst case. The pressure hull failure scenario is the simplest to describe and the hardest to wrap emotion around because there is no sensory experience to report. If a hull fails at Hadal depth, the equalization is so fast that no one feels anything. The brain does not register pain or terror. The state ends before perception catches up. That is not guesswork. It comes from how fast pressure waves move and from what we know about reaction times. For drowning or hypoxia in the upper ocean, the picture is different and slower. There are minutes of struggle, then confusion, then a narrowing of awareness as oxygen drops. Cold can numb and delay, but it does not change the order. When suits flood or masks fail, the sensation is of water where air should be and of coordination slipping. Those are not Hadal experiences in most missions because crewed work at depth uses sealed habitats. The vehicle's design is precisely to keep those problems out of the cabin. Inside a functioning vehicle, the senses also register small positives that matter more than people think. The sound of a scrubber fan is reassuring because it means carbon dioxide is being captured. A crisp response from a thruster tells you there is clean oil in the motor and no fouling at the prop. A stable humidity number means leaks are unlikely. A slight drift of the cabin temperature in the expected direction as batteries discharge tells you the energy budget is on track. These are small comforts, but they add up over hours to a sense that the plan is holding. The human side is not all checklists. People talk. Pilots and scientists share short jokes. Someone describes a fish with a soft tone that cuts tension. A quiet 2 minutes lets the brain reset before the next task. Snacks are simple and chosen to be gentle on the stomach. Hydration is steady but not heavy. There is an agreed rule that nothing sticky or crumbly goes near the main panels. These small rules keep the cabin neat and the minds inside cleaner than they would be if everyone acted on impulse. Decision-making under time pressure is basically triage. If power drops faster than expected, you skip secondary objectives and begin ascent early. If a pump is cycling oddly, you assume a leak and confirm. If the acoustic beacon does not reply, you still proceed with ascent because the worst place to troubleshoot a locator is at the bottom. There is a calm ruthlessness to that order that comes from accepting the remoteness of the environment. You cannot afford sunk cost thinking. If something seems off, you cut it loose and come home. After a dive, stress shows up as small hand tremors when you step onto a rolling deck, a wave of sleepiness, or a headache that resolves with fresh air. People debrief while details are fresh. The tone is factual. What went right? What was surprising? What needs repair? What should change before the next ride? When a moment was scary, they name it and fold the lesson into the next checklist. That cycle is what makes the next trip a little more predictable. One thing outsiders do not expect is how much of the sensory world is shaped by the steep geometry of trenches. On a flat abyssal plain, you can drift and keep a safe altitude without a lot of vigilance. In a trench, you are always aware of one wall and of the risk of another just out of sight. You scan sonar more often. You watch for downslope flows that carry silt or mud. You avoid sitting still beneath a steep scarp. The psychology is more defensive. You are visiting an active slope, not a quiet plain. There is also the background knowledge that even near-perfect crews can get unlucky. A tiny flaw can turn into a big one in the wrong moment. That knowledge does not freeze people. It tempers ambition. Dives that look boring on video are the product of that attitude. They are on schedule, on plan, and light on improvisation. They bring home clean data and leave little drama behind. If the final moments are part of the story, they are either the slow narrowing that comes with a loss of breathing in shallow water, or the instant blackout that comes with a pressure hull failure at depth. Between those endpoints sits a wide space filled with ordinary, careful work carried out by people who listen to machines, trust instruments over feelings, and accept that somewhere outside the window the ocean is indifferent. The sensory world they live in is small and manageable by design. The psychological world is smaller still, shaped by training and by respect for an environment that does not bend. In that space, awareness is focused, choices are practical, and the path home is defined by routine rather than by heroics. That focus and routine have to adapt to the neighborhood because each trench brings its own mix of depth, shape, biology, weather, and logistics. The physics of pressure stays the same everywhere, but the plan you carry on board changes depending on whether you are dropping into the Western Pacific, the Caribbean, the Indian Ocean, or the Southern Ocean. The differences are not subtle when you stack them next to each other. They change how long the descent takes, what hazards you watch most closely, who shows up first to scavenge, how likely you are to strand on a terrace, and how quickly help would reach the ship if you needed it. Start with the obvious heavyweight. The Mariana System in the Western Pacific is the deep end of the pool. Challenger Deep reaches a little more than 11,000 meters. And Sirena Deep in the same trench is only a little shallower. The pressure down there is more than 1,000 atmospheres. That number does not frighten the hull by itself because the hull either holds or it does not, but it narrows safety margins and lengthens the dive. Getting down and back up is a full-day affair, measured in many hours on each leg, with a short working window at the bottom if you want to keep healthy reserves of power and life support. The trench axis is relatively narrow and sits alongside a forearc with patches of very high pH fluids produced by serpentinization. Those fluids show up as bright spots in the chemistry, and you plan for them if your science cares about them. Biologically, the Hadal amphipods are numerous, and Hadal snailfish have been documented around a little over 8,000 meters. Seismicity is frequent, but earthquakes are part of the background everywhere along subduction zones, so the practical takeaway is the same as in other places. You do not linger beneath steep faces, and you respect fresh scarps when you see them on sonar. Logistically, this region is remote. Ships stage out of Guam or Japan or sometimes farther afield. Weather windows compete with typhoon seasons, and permits for protected areas are a real part of the calendar. Slide south and east to the Tonga region, and you meet another giant. Horizon Deep in the Tonga Trench runs to a little more than 10,000 meters, close enough to the Mariana numbers that the same engineering rules apply. The trench is narrow and steep in many stretches, which makes the walls feel closer and the navigation more demanding when you are near the seafloor. The area is highly seismic. That does not mean you will feel shaking on a given day, but it does mean fresh slides are common and turbidity flows are part of the landscape. The Kermadec system to the south has a similar character, and both are places where crews keep a sharper eye on tether angles and thruster loads because entanglement and suction in soft sediment are real risks. The biological cast looks familiar if you have dived the Mariana, with amphipod swarms and occasional snailfish at depths a bit shallower than the very bottom. Logistics are again on the hard end. Transit distances are long, port options are few, and weather in the Southwest Pacific can turn rough quickly. The Puerto Rico Trench is a different experience even before you consider what is on the bottom. It is the deepest point in the Atlantic, reaching a bit over 8,000 meters, which puts the pressure at more than 800 atmospheres. That is still far beyond scuba or habitat work, so the vehicle is doing the same job of holding 1 atmosphere inside. The difference is in access and context. You are a day or two from major ports, not weeks. Flights, spare parts, and medical contingencies are more straightforward. The sea state is driven by Atlantic weather and tropical storms in season, but the ship can often duck into shelter if needed. There is more traffic, from fishing vessels to cargo ships, and that means launch and recovery bring a little more radio chatter and coordination. The trench itself has broad sections with terraces where material can strand, and it sits near productive shelf waters. Scavenger density tends to be brisk when food arrives. For a search, that means the axis can be less of a sure bet than the ledges, and the turnaround time for repeated dives can be shorter because refueling and resupply are simpler. The Java or Sunda Trench along Indonesia's southern flank is deep, active, and messy in an operational sense. Depths pass 7,000 meters in many places and reach near 8,000 in some segments, so pressure is again hundreds of atmospheres. Rivers pour sediment off nearby shelves year-round, and monsoons modulate currents and visibility. The trench is broad and often filled with thick sequences of sediment. That builds terraces and smooth slopes, which are easy to underestimate. A vehicle can land softly and then find itself settling deeper as the mud consolidates, with suction trying to keep it there. The seismic history is famous for tsunamis that affect coasts, but for a vehicle, the seismic reality is that slope failures and turbidity currents are not rare. Biology is abundant compared with remote gyres. Amphipods arrive quickly at any organic source, and holothurians process the seafloor in visible numbers. Logistics are both easy and hard. You are near major ports and workshops, but you are also in waters with complex jurisdiction, dense ship traffic, and strict permitting. Launch and recovery windows need more coordination, and pilot plans are built around reduced visibility and higher odds of soft ground. Far to the South Sandwich Trench rides inside the path of the Antarctic Circumpolar Current. It is cold at the surface and cold at depth, and the weather is unforgiving. The trench reaches beyond 8,000 meters in place, and the bottom water is very close to freezing. The cold slows microbial processes between feeding events, but it does not slow amphipods much. They are adapted and effective. Seasonal productivity pulses influence foodfalls. During rich seasons, there is more organic material reaching the bottom, and scavenger response is correspondingly lively. Storms and sea ice narrow the field season. Ships pick their days carefully, and anyone planning work there builds slack into the schedule because accidents in the Southern Ocean start at the surface long before a vehicle reaches depth. On the bottom, steep walls exist alongside sections draped with sediment, and the plan looks like what it is anywhere else with active slopes. Keep altitude, avoid overhangs, and assume that a clear terrace today can be a buried terrace tomorrow. Head back north to the Izu Ogasawara and neighboring Japan trenches, and you meet a classic steep geometry with a lot of faulting and a long record of earthquakes. Depths reach beyond 9,000 meters in places, and large sections have narrow axial floors with little room to spare. The slopes are cut by gullies and draped with debris from frequent small slides. That combination makes for beautiful bathymetry maps and careful piloting. Snailfish and other deep fishes have been observed in the Hadal zone here, though their exact depth limits follow the same general pattern as elsewhere, tailing off beyond a bit more than 8,000 meters. Amphipods do their usual work fast. Cold seep patches occur in forearc regions nearby, and serpentinite-influenced alkaline fluids have been studied in the broader system, which matters if your science looks for them. Operationally, Japan's proximity makes transit easier, but weather in the Western Pacific is variable, and typhoons complicate scheduling. If you look farther afield to the Kuril-Kamchatka and Philippine trenches, you see variations on these themes. Depths are significant, slopes are steep, and subduction keeps the system lively. Sediment supply differs. Where large rivers deliver mud and sand, terraces get broader and smoother. Where the coastline is rocky and fewer rivers feed the trench, more rock is exposed and slides produce more blocky debris. The practical effect is simple. In sediment-rich segments, the risk of suction and burial during a turbidity event grows. In rockier segments, the risk shifts toward entanglement and impact hazards. One of the quieter differences that shows up in operations is sound. Acoustics carry navigation and short messages, and the ocean's sound channel changes with latitude. In tropical regions, the sound channel axis tends to sit deeper, often near 1,000 meters, while in polar regions it can sit closer to the surface. That changes the ranges at which beacons can be heard and how much multipath you get from echoes off walls. In narrow trenches, echoes are always a concern, but the baseline behavior still shifts from place to place. It is a small detail until a pilot is trying to home on a beacon in marginal conditions, and then it becomes part of the feel of a region. Weather and sea state shape the topside routine as much as anything that happens at depth. The Mariana and Tonga regions bring typhoon seasons that block launch and recovery for weeks. The South Sandwich area brings relentless westerlies and cold, and a calm day is precious. The Caribbean and nearby Atlantic offer more frequent windows, but hurricane season still commands the calendar. Java brings monsoon patterns that flip currents and winds. Those patterns decide how many dives a season can support and how much slack you need in case a system blows through later than expected. They also decide how tired crews will be because rough recoveries and hard nights add up. Law and logistics are less glamorous but real. The Mariana region includes United States protected areas and unique monument rules. Japan has efficient permitting but clear boundaries. Indonesia's waters require careful coordination with multiple agencies. The Puerto Rico area brings United States and Caribbean authorities. These constraints influence not only where you can put a ship, but how quickly you can change plans. For search and recovery, those differences show up as response time, access to ports, and the availability of local assets. In a remote Pacific trench, a spare connector is a week away. In the Caribbean, it could be a day. Biology is where regional character comes through strongly. Trenches under productive waters, like stretches of Java and certain parts of the Western Pacific, support denser scavenger communities. Amphipods arrive in thicker clouds. Isopods and holothurians are noticeably more common. Bones diminish faster because osedacs and associated fauna colonize quickly when exposure is steady. Trenches under oligotrophic gyres, which are nutrient-poor open ocean zones, still process remains effectively, but a carcass sits longer between visits, and microbes carry a larger share of the load between animal feedings. The South Sandwich set runs cold enough that microbial steps are slow, yet animals stay efficient, so the early timeline is still measured in hours to days for soft tissue access. Where alkaline fluids occur, like parts of the Mariana forearc, small pockets of adipocere can form under clothing and in sheltered spots. That detail is a local quirk, not a broad rule, and it comes and goes meter by meter. Geology shows its regional signature in the way things come to rest. Narrow trenches like the Kermadec and parts of Izu Ogasawara behave like funnels. Heavy objects that avoid ledges arrive near the axis more often. Broader, sediment-filled trenches like long stretches of the Sunda region are sticky. Objects strand on terraces and stay there until a larger slide plucks them. The Puerto Rico floor includes irregular fault scarps that catch lines and distribute debris across unexpected pockets. The South Sandwich slopes wear the stamp of repeated small slides, which is good in the sense that energy is released often, but it still means you face fresh surfaces that can fail again after a small nudge. The same physics that makes pressure the king everywhere also explains why depth matters for engineering margins. The step from 8,000 to 11,000 meters increases pressure by a few hundred atmospheres. Designers account for that with thicker hulls and tighter windows on allowed defects, but the cost is mass and reduced payload, and the penalty is longer transit time because a heavier craft descends and ascends more slowly if power is limited. Battery capacity is finite. Lights and thrusters burn energy. The slice of time at the seafloor shrinks at the deepest sites unless the vehicle is unusually large. That is why the deepest dives often carry simple mission goals and short target lists. It is not a lack of ambition, it is arithmetic. Search planning looks different area by area, even though the steps are the same. In narrow trenches, you start near the axis and work upslope, because the funneling effect is real. In the Java-style trenches, you start on terraces where currents deposit and where suction can pin an object. In the Puerto Rico area, you pay attention to side gullies cut by faults. In the South Sandwich, you budget fewer days and brace for weather aborts. The tools are similar everywhere, from side-scan sonar to baited landers. But the mental map you draw bends with the terrain and with the local flow. If you step back and compare, the message is not that one trench is friendlier or deadlier in any dramatic way. It is that each one teaches its own set of habits. Mariana trains patience for long drops, caution around alkaline patches, and discipline around protected zones. Tonga and Kermadec sharpen attention to slopes and tether management. Puerto Rico rewards quick turnarounds and careful coordination with busy seas. Java forces respect for soft sediment and complex permits. South Sandwich insists on conservative weather calls and realistic expectations about how many dives you can finish in a season. The sameness sits underneath all that. Pressure increases roughly 1 atmosphere every 10 meters no matter the longitude. Cold water near 2 to 4 degrees Celsius greets you in every Hadal trench. Darkness is absolute without lights. Scavengers treat carrion as a rare opportunity and respond fast. A pressure hull either keeps the inside at about 1 atmosphere or it fails in a way that ends awareness immediately. Those constants are why training and design travel well from one trench to another. The variations are why the checklists are not identical and why the pilot's instincts are tuned by the places they have flown. So the answer to how trenches differ is that they change the shape of the work without changing the basic rules. Depth stretches timelines and tightens margins in the deepest Pacific sites. Topography in narrow trenches concentrates debris and risk along steep walls. Sediment in wide trenches sticks to gear and steals objects onto terraces. Productivity controls how quickly animals arrive and how long bones last. Weather decides how many chances you get to try. Law and distance decide how complicated it is to keep trying. Put together, these differences matter for any human story that ends or is investigated down there. They decide the likely path to the bottom, where resting places form, how the local community responds, and how realistic a recovery attempt would be. And when you have said all that, the closing truth is steady. No matter which trench you choose, pressure defines the boundaries, remoteness shapes the plan, and the ocean keeps its own schedule.